Hi, my name's Bob Greenyer and welcome to the Martin Fleischmann Memorial Project. I am here this Sunday, the 13th of March 2022, and I am going to talk about something that I'm very excited about and something that I'm not so very excited about, but it presents a potential opportunity. And so we're going to start with that first, but I hope you've all had a very good week, and I'm hoping Dave can join us. Maybe he can't, but what this is going to be a little bit rough. Sometimes I have time to put things together properly, sometimes I don't. This is one of those times, but I think the importance of this data is high, and I think it's necessary to get it out in its raw form. And also the opening comments that I want to make, I think it's important to get that out because I would seek your opinion on direction. Anyway, so what am I talking about? Well, I'm talking about the Fixing Fukushima project, and if you recall, we put together a proposal based on using calcium carbonate and applying electrolyzed water, but using Ohmasa's vibrator system or something similar to produce HHO gas, as it's commonly called, or brown gas, or Ohmasa gas. Ohmasa gas being supposedly the most superior form of this gas, and applying that to calcium carbonate with a view to the calcium in that calcium carbonate absorbing the neutrons and or doing transmutation, producing potassium, and so forth. So that was the proposal, and so last year I went to work with Slobodan Stankovic in Switzerland, and we ran a test on that, and it produced what Solin called one of the signatures of quantum coherent nuclear reaction. And if you recall, it's this like concentric type of wave structure with these peaks, and on those peaks there were also wave pattern, and this is a signature of a coherent matter collapse, a collapse of a coherent matter structure. And actually on those waves we found the production of silver. And so this is the kind of thing that got me quite excited, so we put this forward as a proposal, and I argued in the proposal that calcium oxide was used by Mitsubishi and by Toyota in a process that was replicated, originally proposed by Iwamura. And this is to show that calcium actually played a role in that, and oxygen played a role in this process. And I also found that there was other places where we had done experimentation and we'd seen the synthesis of calcium, and one of those was with the Ohmasa gas on tungsten. And when we ran the tables, we found that the fissioning of tungsten produced calcium as the predominant one of the predominant pair products, along with xenon, for about 56 to 57% of the most common of the isotopes in calcium. And so the point that we found this calcium showed that potentially this was the process going on, and there was no calcium at all found in the starting material. So what happened over the last many months is we found that ultrasonics were in the original Ohmasa gas generators, that the vibrators produced ultrasonics, and that these had these magnetohydrodynamic ultimately, but hydrodynamic pairs, and that this could be part of the process by which the gas becomes very good at doing its transmutation process. But also that the people who've done HHO in the past, they found that this heavy gas normally came as the first flush of gas from an HHO generator. And I hypothesized that this might be because of dissolved oxygen in there, that dissolved oxygen has this paramagnetic nature, and this came from the work of Bockris and Sundaresan from the early 1990s or mid-1990s, where they found that they only synthesized iron in carbon arc discharges underwater if the water had dissolved oxygen in it. The dissolved nitrogen did not produce this fusion product. And so they have a view on how the iron was synthesized in that case. And so it still comports, it lines up with my belief that oxygen is very important. I've discussed how Ritskev said it played a role with capturing these cold neutrino condensates, these magnetic monopole-like pseudo-monopole structures, and that they cause some interesting processes to go on. So the role of oxygen, I believe, is very important. And what I did was, I worked with Dave and I said, look, I think possibly what's going on is that if you have an electrolyzer plate and you vibrate it, now of course when it is producing bubbles, those will collapse to a degree and there will be some dynamics there that will produce sound, and the sound will help the production of dissolved oxygen in the water. So for those people that have got an HHO generator where it's cold to start with, that's when it can hold the maximum amount of dissolved oxygen, and as the dissolved oxygen is used in the process, then you've only got that finds itself dissolved in the water as it moves forward with the process. So the idea was to let's not go to the trouble of making these big vibrator plates or whatever. Let's try and use ultrasonics directly to produce a lot of sound in the environment, in order that some of the oxygen and hydrogen that gets evolved leads to some dissolved oxygen, and that is an ongoing process, and maybe that will prove more reliable at producing this heavy HHO gas, this gas which seems to be the most active component of HHO. And so Ohmasa found that by analyzing his gas, there were very large water clusters somehow were formed. And if you look at Centelli's work, he actually talks about magnetons and that these are magnetically linked, and that kind of makes sense with my own thinking. So anyway, so that's the direction we went in, and David Butelier found some time to do this work and ran some tests, and he said, what should we run first? And I said, let's run tungsten first, because it has this long history of transmutation and disappearance in various authors' work, including David Hudson, ourselves, Mizuno. Obviously it was used in some of the tests by Svyatomenko, and obviously we had this disappearance in the sapphire experiment, and then more latterly in our our Nova experiments. Not Nova experiments, I'll get there in the end. Our Vega experiments in the case of the tungsten wire used by Henk. So thank you to Henk. That was the most recent, and you could literally witness that on the video occurring, and you could see that it was a ball lightning that was doing the work. Now, in what I'm going to go through today, I'm going to introduce a document by Bychkov et al., which I came across just over a week ago, and it has a review on ball lightning processes and the history of ball lightning, and I'm just going to pull a few initial points out of that. But I'm really excited working through this document, and so I will post a link where you can download that at some point next week, and I think we're going to delve into that document a little bit more in next week's presentation. However, the first thing I want to talk to you about is the second response back from the 9 sites. This is a contracted evaluation agency for the Fukushima water treatment bidding process. Now, this apparently has been an ongoing bidding process since something like 2012. It's actually a rolling program, but our view is we have a technology I believe will remediate that tritium water, and the Parkhomov reaction calculator shows that if you have protium, it has a certain level of activity. Deuterium has a higher level of activity because there is a bigger sort of potential well for it to drop down when you are having a fusion. And tritium has an even higher sort of potential well to fall into. And so it would appear that the process would be most vigorous with tritium, and so that's why we kind of the basis for which we put that forward. And so the problem is that we don't have access to tritium, and there is 1.3 million tons of this tritium-laced water at Fukushima, and what we were asking for is, we believe this process will work. We will, at our own expense, if we have the invite to go there, run an experiment with our own apparatus. They can instrument it in any way they like, and we will see, using our expertise and their expertise, if there is the expected outcome in the form of the tritium being remediated completely, not just separated, but remediated completely. And we think, personally, I think that if you have 1.3 million tons of this and you're willing to dump that into the Pacific Ocean at the end of this year or beginning of next, or from the beginning of next, that asking for a couple of litres and some time to test the hypothesis would be worth doing. However, you have this layer of this agency. Now, this agency, 9 sites, they don't only do evaluation for this particular project. 9 sites do evaluation for a number of government projects, I would imagine, and other projects for other companies, where they are the sort of initial firewall between the proposer of a solution to a problem or something that would meet an industrial need and the actual customer. So they have people that are experts in English and experts in technology, and they can assess the potential of solutions. Anyway, so I'm going to just show you what they replied here in the second reply. The first reply was, we hadn't had enough time to look at your document, and that was a couple of weeks ago. And then we got this, and it was, the result of the primary evaluation of the second technology to separate tritium from water treated with multi-nucleoid removal equipment, ALPS. Now, for those that don't know, the ALPS system it's kind of like got zeolites and other processes in there to extract things like cesium-137 and strontium-90 from the water. But because of the nature of the triton, the proton with 2 neutrons in the Fukushima water, this tritium water, it's basically the same as normal water. So you can't just chemically or more simply remove it from the water. So they have this system called ALPS, which removes all of the other nuclides down to a very minimal level. But it can't get rid of the tritium. So this is the ongoing problem that they have there. So this is addressed to Quantum Heat, the organization that runs the Martin Fleischmann Memorial Project, and myself, Robert Grenier. So it says, thank you very much for your proposal for that above. We have evaluated your proposal strictly according to our evaluation criteria, and the result is as follows. Primary evaluation result. We concluded that the evaluation criteria were not met. The reasons for the evaluation are as follows. We could not conclude that your proposal could meet the prerequisite requirements for tritium separation, measurement and treatment capacity, because your proposal did not provide experimental data and quantitative information. What we did provide is the amount of energy that would be required using a system provided either by Dr. Roisin Ohmasa or by Swiss Oxyhydrogen Energy, with the experience, the more than a decade-long experience of Slobodan Stankovic, to electrolyze the water. And in our proposal, we actually had the option that, because they actually had this in other options, where we could use the system that we are using in multiple ways, and one of them was to flare and vent. So one of the processes that they were talking about was to basically electrolyze the water and dump the tritium gas into the atmosphere, and therefore it gets dispersed that way, and because it's lighter than air, it would go up to the upper atmosphere and basically not be a problem for the biosphere. And so there's that, and also you could do what put it up into a vent and then flare it so it comes off as steam. So these are two options that are actually already in the proposals for dealing with the tritium water. And we provided the calculations down here, thank you to Slobodan Stankovic, for based on the efficiency of either a version supplied by Slobodan or one by Roish and Ohmasa. So basically we tied it down to somewhere around the efficiency of these devices and calculated the amount of energy that would be required based on the experience of the researcher. So it isn't the fact that we could not treat in any way the material. And the measurement processes, we suggested that we had Dr. Matsumoto, who is a lifelong nuclear scientist specializing in radiation, and we have Dr. Alexander Parkhomov, a lifelong nuclear scientist specializing in radiation. We thought it might be sufficient to provide the expertise of those two individuals, one Japanese and one Russian, to deal with the measurement side of things. And so what it comes down to is the tritium separation. Now, are they really wanting to... This is a weird phrase for me. Are they really wanting to separate the tritium? Because in some electrolysis processes, what you end up with is most of the tritium being left at the bottom. Or do they literally want it separated? Because that isn't happening if they dump it into the Pacific. That's not separating, that's diluting it more and putting it out into the ocean. So, you have to ask yourself, what are they actually asking for here? And so, surely, if we are producing T2, i.e., like hydrogen gas, but instead producing tritium gas in our HHO separation process, then which will be TTO or THO or TDO, depending on the relative abundance of the isotopes, we are separating it. So we gave the data for separating the tritium. But we have this catch-22. We can't prove the process that we're suggesting without access to the tritium. And what they're saying is we need the data for how this will work with tritium. It's kind of like, let us have access to the tritium. And it's kind of like, is it a charade? Well, maybe not. I don't think it is. And so they say here, if you wish to submit your proposal again, we welcome your proposal with more specific and quantitative information. They had a word in here which they weren't sure about the translation. They added a question mark, so I've put regarding in there. Regarding the prospect for achieving the prerequisite requirements. So the prerequisite requirements are experimental data and quantitative information for tritium separation. So without having access to the tritium, I think the only thing we can do is show that the processes that we are proposing, and bearing in mind, if we are using Ohmasa vibrator plates, then they are already causing fusion to occur and remediation of the tritium in the water. Ohmasa has already demonstrated this with them. So it was something around about 2001 or 2002. He had some deionized water in just the vibration system, and he vibrated it for a number of days, a period of time, and there was this brown sludge at the bottom. So they had the brown sludge analyzed, and they found a vast number of different nuclides had been synthesized. And so when Fukushima happened a decade approximately later, in 2011, he thought, oh, well, it was transmuting this material back in the early 2000s. Perhaps it will be able to transmute the radionuclides and the tritium in the water. And so they ran some tests, and it did something like 2 half-lives of cesium, or it did a lot of remediation in a period of 1 month with a sample of water. And this was videoed. There was a television crew, politicians. This is the story I'm told, from TEPCO, engineers from TEPCO, and they witnessed this, but they didn't publish it. He wasn't allowed to publish it, and so on. So it's a very disappointing exercise. And so, I'm not going to be defeatist about this. I'm not going to say that the whole process is just for show. It's a charade. Yes, we'll open invites for people, and we'll allow this process, but in the end, all we're going to do is dump it into the ocean. And I don't want to believe that that's true. And so I think what we have to do is to do what we can in the absence of anyone supplying us with tritium. Now, if anyone out there knows a supplier of tritium, I highly doubt it, but it would be great to hear if they would be willing to conduct the experiments that we need to do to make this a slam dunk. In lieu of that, in absence of that opportunity, because let's face it, we're not going to get that from Chernobyl, are we? In the absence of that opportunity, we were working in the background to try and prove the process or test the process that apparently had happened in Fukushima could be in Ohmasa gas could be replicated. And so that is, I think, what has been achieved. You may be the judge of this in a different way. But to do this, I want to return to a presentation which I gave to the Russian community called Laena in a can, if I can, and it's not showing me that. So give me a second. I will get that back up in a second. Okay, so here we go. So in this presentation here, right, just before I go on, thank you, John Doe, for your very generous contribution. That's very, very helpful. Oxygen, paramagnetic and giver of electrons, yes. Yeah, well, we'll talk about the Gordon, the reactor structure that was put together by David. Okay, so Mescal has said that he put an ultrasonic fogger into a cell and it looked like the bubbles were clearing faster, but yes, perhaps they were going into solution, and that's one way to look at this. Very, very interesting comments by Mescal. So if you are not seeing this live, I suggest you go onto a laptop or on your phone and look at the comments. Actually, the comments are always wonderfully valuable. So I thank you for everyone for their considerations in the comments. Okay. Yes, TP Sven, I think that's what they might want to do. Tritium and deuterium are... I know there's some sort of ionic or sort of membrane-based ways of harvesting deuterium now, but that isn't an option for tritium. But realistically speaking, there's two uses for tritium. One is a bomb, and one is possibly for a fusion reactor. In the fusion reactor of ITER, they are using a lithium blanket, and the neutrons that come out of the process cause the lithium to split, producing tritons, tritium. And so they hope to breed the tritium in the reactor using the neutron absorbing blanket, as it were. So, but it's impractical, really. You need a nuclear reactor of some sort to produce tritium in any meaningful quantity. So the tritium would be incredibly valuable if you could separate it. But given the fact that they've already signaled they are building this tunnel, and that they are in absence of any other practical solution, they are going to dilute it with seawater and dump it out a few kilometers out to off the coastline into the ocean. That isn't separating the tritium. So this is my point. My point is, we ask for access to the tritium so that we can show the process. We're not asking for them to pay for that. We're not asking, we will go there with the equipment, with the Ohmasa vibrator, if that's not available, with Slobodan's device, or maybe even with a device made by whoever. It doesn't really matter. We have this Yul Brown BN 2000 that actually, in my understanding, is it's going to be worked on this month. We have several options to test, but we can't test it if we don't have the tritium. I do have one proposal I've given to David, and it's going to be expensive, but we take manganese sheet, Mn55, and we do what was shown by the wonderful Ukrainian researcher Vladimir Vysotsky, who worked with the Russian researcher Alakorninova, where they took manganese Mn55, it has a single isotope, and they used deuterium water and a syntrophic colony of bacteria and yeast, and the bacteria and yeast then added the deuteron to the Mn55, making iron 57, and they used then the nuclear magnetic resonance of the rare isotope of iron 57 to show that they'd done transmutation and that the iron could not possibly have been a contamination because of the output from it and the ratio of concentration. So if we could get some Mn55 sheet or powder or something like that, and then have basically deuterium electrolyzed, and we put that on there. Do we produce iron? If we do, great. That is something that's expected in Laena. You can go to iron quite much more easily than going beyond iron, because you have to put work in to a degree. Then if we see Mn57 in high abundance with ICP-MS and also record that with a nuclear magnetic resonance, then we will have 100% proved that deuterium can do that. If you do it with light water and you don't see that production of vast quantities of iron 57, but you do see just iron 56, that is a proton onto Mn55, then so you don't see this NMR signature of the iron 57, then you can show that it is adding the hydrogen isotope to the manganese, and that is the process that's going on. It is not contamination. So, but this requires 3 different analytical tools, which are all expensive and so forth. It would just be easier if we could do the job that we needed to do, rather than prove beyond any possible doubt that Ohmasa gas or HHO or the gas, whatever the gas is that's coming from David Boutlier's embodiment, that is doing precise transmutation of proteons, protium, deuterium, or so forth. So it shouldn't need that much effort. We just need to get on a plane, go over there, give us a couple of litres of your nasty stuff, let us run it through the electrolyzer, 1, burning it directly, 2, then onto calcium carbonate, going to calcium oxide, doing the limelight business, and either capturing those neutrons or synthesizing potassium and so forth, and helium. And so that's what we would like to do, and it shouldn't be this hard. It shouldn't be this hard. Yeah, John, it's frustrating. It is frustrating. However, you what you're trying to do is you're trying to lead nuclear scientists and engineers and politicians, who all have been taught that this is impossible, over that intellectual hill of it is possible. And the implications are unimaginably phenomenal. And so you have prejudice, you have pre-learning, you have not only the barrier of a organisation that's required to evaluate things for their validity before passing them on and bothering the people that have got big salaries and, you know, little time to evaluate these things. You don't want to be wasting their time. So you have this firewall. So you have layers of firewall built onto other layers of firewall. And all we're asking is for the chance. And if you give up, that is the point at which you guarantee failure. So we cannot give up. So we must do what we know we can do whilst working in the background to improve the base and the solidity of the science, so that the argument becomes more and more and more convincing. But given the fact that Yul Brown was saying you can take whatever in the 1980s and you can convert it into carbon, and demonstrated to politicians that you could remediate nuclear waste near instantaneously in the 1980s and 1990s, you know, it is a huge uphill struggle. But back then he was coming from a point of protected IP, from a point of I want to make big bucks from this, and there isn't a intractable problem that has to be solved. Otherwise, the Pacific's going to get a big dump of radioactive waste. And you know, there is one other issue here, that they have made a lot about the level of other nuclides that are in that tritium water. There is one thing that you couldn't say, but it might be the case that the tritium water itself isn't as clean as they have said it is. I'm sure it is, but you know, there are all kinds of reasons why you would not want that to be public. And so if you gave an independent body access to the tritium water, and it turns out the tritium water has a lot of cesium-137 output coming from it and a lot of strontium-90 output coming from it, no one would allow that to be dumped into the sea. No one. So have we got this extra layer of we can't give access to this material, so we're going to have people prove absolutely certainly with their own source of tritium that this works before we will allow the industrial units which are already proven to work to be sat and fed our water, and we won't discuss the rest of it. My view is I actually don't care whether it's got trace levels or much higher than they are claiming in the water, because I'm of the belief that either they will be left as a concentrated residue in the unelectrolyzed water, or they will actually be dealt with by the HHO. Just like is apparently and seems to be the case from Yul Brown and other people that have explored this. Yeah, you can buy tritium keychains, this is true, but you're talking about an incredibly small amount of tritium. So, you would probably need to spend a phenomenal amount of money getting those glowing tritium keychains and then producing triated water from that, and then measuring the activity of that, and then it's nasty. Right, okay, so anyway, so Laena in a can was the presentation, which I have here. And we talked about the phenomenological aspect of that, the fact that oxygen is the number one most abundant element by far in the atmosphere and in the crust, rather. This is the crust, and silicon is the second most abundant. But notice also, when we look at the data that I'm going to show you today, aluminium, iron, calcium, sodium, magnesium. I am arguing that the process that is Laena, which I believe occurs, and other authors have said this, occurs in cavitation, but also occurs in anything to do with lightning, and any highly energetic process that leads to charge separation, which may lead to vortexes, and the vortex produce magneto-hydrodynamic structures, leads to this process. And these elements here, I think you're going to see these, and we have seen these in our work. And so is it that the crust of the Earth and the atmosphere of the Earth is caused by these processes? I believe they are. Okay, so and I give my phenomenological arguments there. And you can go and see that in another presentation. I give examples from Leclerc and from Adamenko. Then I actually talk about the fact that Langmuir in 1909 was effectively doing HHO because there was some residual water in his reactor, which was actually just a light bulb. And we know now from tungsten filament light bulbs, work of Dr. Alexander Parkhomov, that they appear to be producing something that is causing the emission of particles that are changing and doing transmutation of material at a distance. And so that would be, in my view, the strange radiation, but the strange radiation is coming from the nuclear reactions that are going on, and it is HHO generated by water in the tungsten filament light bulb that causes this gas production. I believe the gas was the production of protons. So that was HHO. I talked about Wendt and Irian, and they had the decomposition of tungsten. And that was with an electrical discharge. And then I talked about this is that work there, and the work of Simon Brink, and also this is the one by Mizuno, where he had this explosive event, and he calculated a COP of 800 times. Again, this is HHO. This is HHO by Simon Brink. None of these people were calling it HHO, but it is HHO. But this, I think, is probably the most significant work here by Ruitskev. It is HHO, and this is important because the second thing that I'll show you tonight is a replication, I believe, of to a degree, of the observation of titanium. And what was Ruitskev doing when he saw strange radiation, ball lightning, established that there were pseudomagnetic monopoles or monopole-like structures on iron 57. He was exploding using an intense rate of current change, causing the exploding of foil. And then the foil was titanium in there. It was titanium. So we are going to, and because it's titanium in water, this is basically a bringing together of the Wendt and Irian exploding metal foil or exploding wire and HHO. It makes you will get water splitting here, and it's made and it's destroyed immediately. So this is essentially what you're seeing in Simon Brink's work and what you are seeing up here in Langmuir's work. It's all the same thing. It is HHO. Okay, so and you've got the whole thing here. The ball lightning, as I said, the strange radiation. This is the emitted thing from your metal that's going through this extreme event, and so forth. So there we go. And yeah, so this was the paramagnetic nature of oxygen playing a role in the failure at Chernobyl, and this is talking about the change in optical transitions, so the photons emitted are changed. This is ball lightning producing the pseudomagnetic monopoles, and this is from this source where you have a discharge through water producing the plasmoid structures. This is a red one, and these are the typical colors that you get. There's a kind of bluey green one here, and you get north and south poles here, and so they're coming together, north and south here, north and south, whereas in this one where you had a high energy electrons coming out of a synchrotron going through a conversion target, which itself may be tungsten, and then the magnetic field here separating out the electrons, just allowing only the gamma rays to pass through. It's not just the gamma rays. The gamma rays are darkening the X-ray film here, but above and below, where the gamma rays are not falling because they're occluded by the magnetic poles of the magnetic field that's doing the separation of the electrons. Outside of that, you are getting these same exact structures that you get in this plasma flow discharge. But in this case, if you look, he's deliberately circled this one, and this would be on one of the poles, and here you have effectively two of the same poles. So if this was deflected by the north or the south pole, let's say this was two south poles, they are coming together back to back, right? Whereas over here, where you've got a mixture of north and south poles, they're coming head to head and head to head. Okay, so And you can understand why this would be, is that in this case, the whole head is, let's say, north, and the whole head is south here, whereas you've got a very fine focus of a north beam out of here, sorry, a south beam out of here and a north beam out of here. So this is a south head and this is a north head, let's say. This is a south beam and this is a north beam. So the heads come together because they express, whilst it's a weaker field, it's not a highly localized focused field. Okay, so the heads come together, but when you've got these ones that are of the same pole coming down here, they come back to back. Because you know that it's north south. It's just the way it's working. So the only way these can join together is the top, even though it's a weaker, more spread out, it has to find the opposite pole, which is the focus beam that comes out of the back. And so I said in my presentation in ASTI, I did not believe that Bogdanovich, when he chose to circle these two features from these two respective experiments, was not doing it deliberately. I said that this was an Easter egg, like a programmer's Easter egg, where they are showing something that is exceptionally significant in this finding. And this supports the work of Perovskov and the work here of Roitzkiev. And so let's focus on I'm going to skip down to where I'm talking about vibration. So there's Yul Brown again, it's HHO, and just for the sake of the record, you have Matsumoto here. And Matsumoto is using potassium hydroxide, and we've chosen potassium hydroxide for the same reason that Matsumoto chose potassium hydroxide in our experiments with Dave Butelier, because the carbon that came out of this lead ball, this bloom of carbon, this 12 and 13 nucleons coming out of this 204, 6, 7 and 8 nucleons of lead ball, coming out of a pole of this structure, is because if you used potassium hydroxide with lead and copper and light water, there was no carbon in the process. So the carbon synthesized here is from fission of the lead inside this ball, and it's coming out of the pole of this ball as it did in this ball. But because he was using electrolysis in his process, it was HHO. So he was both making and destroying that as he was doing the experiment. And that's just the reality. Okay, so then we have the vibrators of Dr. Roy Ohmasa with our vibrator plates. Now these, if they were doing the electrolysis version, you have in the patent a series of perforated electrolyzer plates, and the vibrated water travels through those, so it will naturally produce solitons as it goes through those perforated plates, in the same way that I believe it was occurring in the work of Leclerc. And so you're automatically getting the forming of solitons anyway in hydrodynamic terms, but also that would accentuate the flow of the water through the electrolyzing plates, the production of dissolved oxygen, which I believe is important to the process. So we established that it was ultrasonic. We had these spots on the plates, and the spots in the plates showed themselves to be hydrodynamic structures, which I've argued are magnetohydrodynamic, and they led to these spiral formations coming out of the cavitation spot, and so forth. And so we presented here. Now, there's one other piece of data I want you to hold in mind, is that in the palladium coated plate, we had our cardioid, our figure of 8 structure, and in the center there was this transparent crystal, and it turns out that this was a nitrogen impure diamond type structure, and that this was surrounded by magnesium, double diamond, and chromium. So there's a vortex pressure gradient going on around the core of this structure, and as I'm saying, one is making and the other one's breaking. And so as this is coming down to carbon in the core, maybe this is breaking, so it's breaking it into carbon, and then it's coming out, and as the pressure the decompression is different, you end up with higher nucleon-based elements coming out of this one. So this is the breaker in this case. But the important thing I want you to note here is that this is in a system, and you're ending up with nitrogen in this core here. So something interesting is going on in this system, which is yielding nitrogen. Okay, so there's that. And what else do I want to discuss here? So the experiment that we did, that we may have recently been able to replicate, but in a different system, is this one. And if I click this, you can see the whole experiment. I think it's going to let me do that. Yeah, so here we go. You've seen this before, but just for record here. So we have the tungsten welding rod here. I believe it's 3 millimeters. I think the key point here, which we haven't got from David yet, because it was just an initial test, is the distance of the HHO jet, in this case Ohmasa gas jet, from the actual target sample, the tungsten. And that is important because different parts of the jet have different amounts of oxygen, hydrogen, and OH radicals. So you can see here, there's the blue area here. That's actually extends to a certain distance, and here we're just slightly beyond, and now we're further. We're quite double the distance from the blue cone here initially, just kind of warming this up, and then you'll see that the chap applying the gas here comes in much closer now. He's much closer. So this is actually critical, because what happens when you are closer is different to when you are further away, and this is something that we need to control for in further experiments. So you may run the test 20 times, but depending on the distance, see, he's very close to that. Now the reason I had in the background here one of the world's experts in ball lightning, Dr. George Eagley, who accompanied me to Japan. I asked him to get the vacuum cleaner and one of these face diapers we're all very familiar with, and capture the fumes, because it had never been done before. If it had, it'd never been published before. So not only did we not have the transmutation data from these kind of experiments, we didn't actually have what the actual constitution of the vapors were. And the old argument was that these vapors were actually literally vaporized tungsten. So then the assumption was that the temperature that the HHO gas, the Brown's gas, the Ohmasa gas was getting to was in excess of 3,600 degrees centigrade or whatever, higher temperature than the temperature on the surface of the sun. And so I was unimpressed by that assumption. And when we applied the bolometer to the Ohmasa gas exposed tungsten, we weren't seeing anywhere near those temperatures. So I was kind of, in my mind, I was thinking, well, this looks more like fumes. It looks like it's maybe, my view was it was blowing up the material, and what you're getting is fragments coming off. What is in those fragments? Well, firstly, we established that there was self-mazing going on in the OH radicals, and this was consistent with Slobodan's observation of an OH peak in his experiments. This is the actual tungsten you saw in that welding rod before, and it had essentially a small amount of carbon on the surface in this area here, and in this little crack here we see the thorium, because it's a thorium doped, 2.5% thorium doped rod, but essentially it's almost all tungsten with some oxygen and carbon. But it's a low concentration of carbon. Okay, what do we see in the aftermath? Well, we see carbon, oxygen. Oxygen is the most abundant element in the Earth's crust. Okay, and here we see 53, 55. Percent, so forth here. So very high concentrations of oxygen. Remember, in those top sort of 7 elements in the Earth's crust, you had sodium, magnesium, aluminium, silicon, calcium, iron. So all of these elements are in the top elements in the crust, and we talked about the fact that sulfur here, which is in this case was 3.9% roughly, this is double oxygen. So if you got some fission going on producing your oxygen, yeah, and then you fuse 2 oxygens, you end up with a sulfur. And a similar story to get to you know, potassium here and so forth. So and you see also some titanium here. Okay, so this here is showing the fission elements of a heavy element are most of the elements that are the top elements in the Earth's crust. Let's go back to that. Here, oxygen top, silicon next, aluminium next, iron, calcium, sodium, magnesium. Okay, constituents of the Earth's crust. And what do we see here in the fission products? Now, I know what people are thinking. Well, if that's the most abundant elements, could that be the contamination? Well, yeah, it could be. But why is that? Why are those things the spherical blobs at the end of plasmoid channels in the material that you have here? So, like, if you follow the plasmoid channel, you have a higher concentration of carbon. Okay, at the end, you've got a bunch with the spherical blobs at the end. You have the elements that are the most abundant elements in the Earth's crust, but at the end of the plasmoid channels. So you can literally see where the plasmoid channels have gone. They've left a trail of carbon. So that's that. And you know, again, the same sort of thing here. You've got carbon, oxygen, magnesium, aluminium, silicon, calcium, iron. Okay, and again, you could say, oh, this blob on the surface is just contamination. But essentially what happened was, you saw the experiment. It went from that straight into a plastic tube, and they stayed in that plastic tube until it was put on Alan Goldwater's SEM at his Magic Sound Lab in California. Okay, and then there is this structure that we've talked a lot about recently, and this is the magneto-hydrodynamic structure and the overall Ohm form here that we've created in various systems, and other third parties have effectively created, whether they realized it or not. And this is the maker, the destroyer, and it can literally synthesize from what appears to be nothing all the way through to make what is something into what would appear to be nothing. Okay, so this is not contamination. This is a very, very specific magneto-hydrodynamic structure, and so we move away from that. But then I didn't stop there, because if we go through, and I've got the analysis here that I've talked about in the past. Here are the elements that are in the chunks of material that were caught in between the carbon, high carbon content fibers of the face diaper. So the face mask. So here you can see the fibers of the face mask here. And these are a bunch of chunks that have been caught there. And you can see in these chunks, so what have we got here? This one here is 1226. Is 126. This chunk here, it's very, very homogeneous, this chunk. It's very, very homogeneous. But in it, you have atomic concentration, 67.48. Oxygen, 24.67. So the triple alpha and quad alpha constitute the vast majority of this entire chunk here. Okay, then you have sodium, aluminium, silicon, potassium, calcium, iron. There we go. And at atomic concentration, just 1.17%. It's a homogeneous blob which has 1.17% tungsten left in it, right? This one here, this is 1227 here. This blob, which is more of a fragment anyway, that has even more carbon in it, less oxygen, and silicon here. So silicon and oxygen. Anyway, there we go. So that is what you see there, and here is a map for it, and so you can see the fragments in here and their relative abundance of elements. And so that is that. So, and I was arguing that as these things move around, the predominant element that's available is present in all of these structures is calcium here that were analyzed on this. And what I believe is that tungsten is a very dense element. That's heavy. That's why people coat them in gold and pass them off as gold bars. It's very, very similar mass to gold by volume. And so the fact that you've got calcium in here, the atomic volume, let's say, of tungsten, and I've shown the graphs for this in the past, let's say is 10 or so, or 10 or 15 or whatever, I think it's 10. The atomic volume of calcium is 25. So if you get one atom of tungsten going to calcium and xenon, forget the xenon, the fact that it's a gas and its atomic volume is absolutely, completely massive. Just calcium would be 2.5 times the volume. So if you get 1 million tungsten atoms and you just forget the xenon again and you make 1 million calcium atoms, they're going to be 2.5 times bigger. And when they get their electrons back, when the coherent matter structure collapses, that's going to cause the electrons will be freely given by the tungsten because it's highly conductive. You end up reforming the calcium atoms, and that produces a Coulombic explosion, which is phenomenal. And that is, in my view, why you see these chunks of material being blasted away, and it comes off as these fumes. Okay, very, very readily. Okay. So that is probably all I want to say about that. Yeah, so we have our ball lightning here, which we might mention. And then later on, we're going to look at the titanium here. So first off, I'm going to deal with the tungsten replication. We're going to look through the actual data that is pretty raw, and I haven't processed it any way, but so I'm just going to... This is as Alan Goldwater sent it from his Magic Sound Labs. And here it is. And so it's got his comments on there from his perspective. And so this is the first of the samples. And this one is tungsten wire analysis. I don't believe this particular one had Ohmasa gas... ultrasonics applied to it. But... what I can say is we don't know whether it's the first flush of gas, so that might be important. Anyway, this is the tip of some tungsten wire, and around the tip there are some cracks, and these cracks were analysed. So for all tests, the samples were mounted so that the areas under study were in free space outside of the mounting stub and its sticky pad. Therefore, the carbon content shown is not a result of beam scatter artifacts from the sample mount materials. Okay, so what is he saying there? Well, basically, you have these little stubs, which these Ted Peller, these little platforms on which you put your sample. And if you put the sample on there, you can have electron beams coming in and scattering and then reflecting back X-ray photons. If you've got like a carbon tape on there and you've got an aluminium platform, then you can get carbon and aluminium apparently in your sample when it doesn't exist. So what he did was he stuck it onto the platform such that the piece of wire is hanging over the edge, and so you don't get any of this reflection problem. So what you're seeing is real data rather than an artifact of your process by which you're doing the analysis. So tip of the W wire, tungsten wire sample with HHO, but without ultrasonic treatment. So, but again, we don't know whether this is the first flush, and more tests need to be done, I believe, to confirm this. But what are we seeing here? Well, at least in one example here, the 2285, which is up here in this top left hand corner here, which is on the edge, and you know, you can see it's a dark patch, but it's blending itself into a lighter patch. Let's see what we have there. Well, we have carbon, which in this case is zeroed out. So what he's done is, for this analysis, the carbon percent was suppressed, giving a measurement sigma of 1 or higher for calcium or sodium. So the reason you would do this is because, as I showed you before, the carbon content can be so high in this material that gets synthesized. We know this from Yule Brown, we know this from Matsumoto, we know this from our own work, that and from Solin and from other authors, that it drowns out the other sample ratios. And so what he's done here is basically, let's say this was 70% or 80% carbon, as I just showed you in the previous work of the analysis of the Röschen Ohmasa material. He zeroed that out so that the other observed elements are more prominent. So you can see here oxygen again can be very prominent. Here it's basically 83%. So I would suggest that if you had carbon here, you would see that this, just like in our previous analysis, it would basically be mostly carbon and oxygen. But what else do we see? We see sodium, aluminium, chlorine, potassium, calcium. This carbon, oxygen, sodium, aluminium, calcium, these are highly abundant elements that you see synthesized in these processes. So you can see here in the element maps, thank you Alan for doing these, you can see that, for instance, here you have the tungsten is behind the area here, all around the way around the front of this sample. You have the carbon synthesized potentially. Now there is carbon in the source material. Okay, so one argument that Alan made is potentially it's not causing the melting or the emission of the carbon. But, you know, if you have a very high temperature carbon with a highly enriched oxygen source in an oxygen environment, one could argue that that would oxidize and form carbon dioxide and go off. So this is being done in free air with a highly oxidizing potentially flame. And so, yeah, anyway, that's a potential thing that you might want to consider. Okay, and there appears to be this calcium here. And the calcium seems to be kind of co-located with the carbon. And we've seen this before. We saw carbon, oxygen, and calcium in the flux loop in the triangle in the Laena reactor. Okay, so again, you can see here, if I zoom into this, we have carbon here, okay? And on the run of the carbon, you have calcium. So I would buy the argument potentially that carbon could be an increased concentration of the carbon that was at a much lower concentration in the starting material, if it wasn't like in the same runs as the calcium that we see here. So it looks like where it is synthesizing the carbon, if we're to assume that it is synthesizing, it's also producing the calcium, okay? Carbon being triple alpha, calcium being dec alpha, okay? So he actually samples here some of the tungsten a little bit back from the head of where the interaction is going on, and you can see there that it is much higher, and this is by atomic concentration, okay? So if it's atomic concentration, the atoms of tungsten weigh much more. So mass-wise, there would be a lot more nucleons. There would be a lot more mass in the tungsten here. Okay, so anyway, there we go. We've got our blobs there. Now, he found this blob a little bit further back from the head. And this is in the kind of area a little bit further away from the main action where we observed this structure. This is not in the main action structure. This one that it's now gone. This one here, our cardioid structure. This, this overall structure here. This is not in the main area, or it's a little bit further away from where the main action occurred. And I believe that maybe at one point a plasmoid was formed, and a ball lightning was formed, and it broke up, as was observed by Oroitskev et al. Many times in their exploding titanium foils, where they had ball lightning appear above and outside of their explosion chamber, and then that broke up after a period of time into smaller ball lightnings, a bit like the smaller ball lightning that did the conversion of oxygen on the top of copper to sulfur in the 10 yen coin. And this maybe touched down and then got stuck on this piece of tungsten and did this transmutation, and as you see in the elements of that, if I can find it here, What do we have in this structure? Well, we have carbon, oxygen, aluminium, silicon, sulfur, potassium, calcium, iron, and even tin in this particular structure here. And if you look at this point, what I'm pointing to here, this is this nodal area here. This has got 50% roughly carbon, 33% oxygen, aluminium, silicon, calcium, and iron. 6.14% iron. The highest concentration is this kind of off-center sphere blob that we also saw on the structure from the 225-day reactor of Dr. Parkhomov, which we analysed, the pretzel, as I called it at the time in my presentation at ICCF 22. Okay, so so going back, I'm not so certain, but this kind of does look a bit like a cardioid structure. I don't know, not overly convinced, but maybe. And if it was, I believe that this would be a similar kind of thing that came off from the main action, and it was a subplasmoid. And if you remember the work with Slobodan Stankovic, when we were applying the Ohmasa gas, sorry, his HHO rather, to another tungsten welding rod, you saw these little blobs forming, and then they were kind of moving around. And he saw this in his own work on carbon rods as well, where you saw these little spheres, and they kind of like they form, and they're able to stay as a sphere in the jet of the gas and then move around. And I think potentially this is one of these coherent structures that's come off to one side. But what do we see in this? Well, we see carbon largely, oxygen also with concentrations, not tungsten. The tungsten is the substrate of which you're seeing it on. Silicon in blobs, and you've got aluminium here in blobs, calcium in blobs, and it actually almost looks like this is a kind of a star type structure a little bit. I'm not overly convinced, but here he's taken some sample points on here, and we can see all our favorite elements here: carbon, oxygen, sodium, magnesium, aluminium, silicon, sulfur, chlorine, potassium, calcium, titanium, and iron. Okay, so all of the elements we saw in our previous experiment with Ohmasa gas is present here in this experiment. And I spoke to you about before that if you actually synthesize fluorine, then fluorine helps you get, because it's 19, you add an alpha particle to 19, you get sodium, okay? And you add an alpha particle to sodium and you get aluminium. And you add an alpha particle to 27 and you get, what is it? Oh, God, I think it's phosphorus, but it's not there, is it? It's 31. 27 plus 4 is 31. Yeah, so, but then you can jump to chlorine, I think it is. But at that point, you start to need some neutrinos involved. But of course, there will be neutrinos involved because these reactions will yield thermal temperatures that are in excess of the necessity of 1000 degrees centigrade to form a cold neutrino and antineutrino pairs. So this observation, I believe here, if this is in fact one of these cardioid structures that forms potentially outside of the main zone, as it did in the case of Ohmasa gas on tungsten here, I believe that we are seeing potentially a similar structure here, but with the blob on top. And in case this looks familiar, this is more like the structure that was in the work of Thomas Claytor and Roger Stringham, where they were using sound. They ended up with a blob on top of the I think it was nickel or something foil, where they had, guess what, these kind of elements forming. Okay, there we go. Okay, so let's have a look. Is there any more here? Okay, so this is a different experiment here. So this is repeat EDX at identical locations. A different algorithm was used for carbon concentration measurement with little change. So yeah, so basically same kind of observations there. Now, I will say that normally when you're looking at EDX, if you see a concentration like 0.39, 1, 0.29, 0.25. If you do enough samples, you can say that it was there, but some people say, well, it's not high enough concentration to actually argue that it was there. And that's why Alan took the decision to remove carbon, so that you had more an element confirmation on the other elements. But because I think he did that, because we've seen it before, because it's been seen by other authors in systems, whether they knew it or not, were actually HHO systems. I believe these are real synthesized elements. I think they line up with what you find in the Earth's crust, and therefore because I believe the processes that cause Laena are the same processes that cause the constituents of the Earth's crust, then I feel that is probably accurate representation of what happened. Now, in this case, there was a fine tip, and he was using ultrasonic treatment in this particular generation of the gas, and I'm going to show you the actual equipment in a little while, and I will probably in between looking at the tungsten sample and the titanium sample. But you can see that, let's say the jet was coming from here, there's this thing that's been caught in the wake. And what is this thing? Well, if we look at it, it appears to have carbon, aluminium, and calcium in there in the wake. Now, again, you could argue that carbon was being vaporized from the front here, and it was then being wrapped around and caught in the fluid dynamic wake. Maybe that is the case, but then you have to argue why in an oxygen-rich environment, which is causing massive amounts of tungsten oxide to form, why there was no carbon dioxide forming. Maybe the affinity of the tungsten is so strong for the oxygen, or rather the oxygen is so wanting to get buddy up with the tungsten, the W2O3, that it leaves the carbon for dust. And that could be an argument. But then where is the calcium coming from? So again, you can see the calcium here. You can see it in these the bits on the back side here. If I zoom in a little bit closer, it might be a bit clearer. So yeah, carbon, calcium, but also silicon seems to be pretty much everywhere. Sometimes when you see these things, if it's everywhere, it's nowhere, because you can see that the same with the tungsten here. Yeah, so that's that, and he's done some spot samples here. Thank you, Alan Goldwater. And again, I believe the tellurium here is actually a X-ray overlap. Possibly with tungsten, I can't remember, but anyway, I don't think there really is some tellurium in here, and to be honest, the level is so small at 0.09, you can pretty much discount that. But you can see the carbon here is extremely high, 90% by atomic concentration, which is, you know, really high here. But you're also seeing the calcium here, the sulfur, which as we know is double oxygen, aluminium, and so forth here. Now he's looking at this area, reference measurement of the ultrasonic treated tungsten wire about 2 millimeters back from the tip. So you could argue there could be deposits here, but anyway, when we did the reference on the tungsten that we did in with the Ohmasa gas, it was miles away. I mean, it was like centimeters away, completely untouched by the gas. But in this case, it was 2 millimeters back. So I do believe that there could have been some vapor deposition here. But anyway, you can see that there is none of these other elements there in 3 sample areas. There's literally no other elements apart from tungsten, oxygen, and carbon. Okay, so there we go. So that is the first test there, and then there is some more detailed tests here where he's going into areas and looking at areas around these features and so forth. So again, it's more of the same story. You've got some iron synthesized here that we observed as well. We've got titanium and so forth. So that's go up to the top here actually. So this looks to me like tungsten oxide. Okay, you get to recognize these things. Now, cracks themselves are a good place for concentration of itonic clusters, according to Matsumoto. And I'll discuss a paper which is very significant to what we're doing in the our other experiments. But nothing too special there. And it just basically, when you look at this area here, it comes out basically tungsten oxide with some carbon. where there is a crack here and there is a crevice here, this gets a little bit more interesting, and you get these other elements showing themselves, carbon in that crack and here. And what I like about this also is, again, you're seeing this carbon here and you're seeing the calcium co-located, but at the end of this carbon line you're seeing the calcium. So at the end of some sort of channel potentially, or some sort of track, you end up with this calcium blob, as it were, and you can see here there's oxygen there, so it's a calcium oxide here. So the oxygen is occupying a much smaller space than either the carbon or the calcium. Is that significant? Maybe, maybe not. Maybe this is looking around on that blob area, potentially a little bit closer. But again, it's telling the same story. These are the elements that you see in the Earth's crust. More of the same. Yep. So another area looking at various points on it, and these are spot samples. I'm not a big fan of spot samples. I tend to like to use area samples because they give you a kind of overview of what's in an area. Spot sample, you know, some people joke that you can always find what you want if you do the small enough spot. But in this case, it's around this. I think this inclusion. But again, it's the same thing, and you've got silicon here up to 4.22% here, 4.75%, and in those areas, this is where you might see some iron. Yeah, so okay, so if you're getting the silicon forming, you're getting close to having iron forming. So you can see with the high concentration here of the silicon, you're getting 4.43 here on iron, and in this case, in this particular blob, there's a 14.82% atomic concentration of aluminium. So yeah, it for me, this is a replication of the Ohmasa gas test. It doesn't seem to be as intense because you're not getting these deep channel bores going on. But this is something that I think many people could explore. Okay, so I think at this point, Bob, I'll fund a tritium night site if that gives enough sample. I don't know, but at the end point, at the end of this, we need to. It's an ongoing process. So if we can convince them to allow us to access their tritium-laced water by showing the fact that we can replicate in various systems the same type of transmutations that have been observed in the past, and we can do it every day of the week, then they might have more confidence. So I think it wasn't sufficient to point to the Japanese data by Iwamura. It wasn't sufficient to point to the Japanese data by Takaaki Matsumoto. It wasn't sufficient to point to the data by Leonid Oroitskev. It wasn't sufficient to point to the data of S.V. Adamenko. We have to be pointing to our own data. Okay, so I think we need to have we need to expand our verification and also test null hypothesis. So what I will do is probably this week I will take this data and I will lay it out in the blog, and I will ask for people to put forward proposals for how we can drill into this and come up with much more qualitative and quantitative data that really nails the fact that this process is going on. As I said, I would love to have an SEM. I've appealed to a number of people so that I could run the supernova experiment and immediately do testing on before and after. I could run ultra experiments, immediately do testing before and after, do the lead wire potassium hydroxide in light water with a copper accretion counter electrode, and do the testing immediately after in an SEM, so that we would just have a tsunami, for want of a better word in this instance, of data that supports previous authors' work, but also, you know, I mean, it's getting to the point where it's just too easy, and it gets frustrating because you think, well, why is no one interested in in actually pursuing this? And you would think that having to deal with that 1.3 million tons of tritium laced water, and possibly with other elements in there as well, at an unknown ratio to us at least. That would be enough of an argument to go ahead with it. Anyway, so I'm going to show you the schematic that David kindly put together, and then I will also show a drawing of the device as well. Sorry, some photos of the device as well, so that you can get a better idea. Before we do that, I'm going to just show you a couple of images of the tungsten wire up close in a little bit better photography here. So you can see what I was talking about there here, that this is the tungsten oxide, and this is this carbon and calcium sort of wake that's coming over, and you can almost imagine the fluid dynamics going on here that's laying this down. It's rather a nice sample, actually. I find it quite attractive as a thing. This is the tip with looking at it at a greater distance, so a lower magnification. Okay, and here this is the non-ultrasonically treated one, and again this is the tungsten oxide structure that you can tend to see, and here is this interesting series of elements that were found up here that we found in our Ohmasa gas, and this is the kind of, I believe this is a kind of cardioid type structure. I think this is I believe this is possibly one of these offset from the main action ball lightning type structures that came out and did its work at a distance, and this, you can see this is on that structure. So you can see there's the tip which we looked at, and this is this structure that's off at a distance. Okay, so you can imagine the main action was going on here, and something formed over here. Okay, all right. Right, so in terms of how much does the SEM cost, it costs the one that I'm looking at, which would be, it's not, what I like about Allen's is it is a fairly large stage. It's not as big as the stage. So for instance, the one that I had previous access to but don't now at Maastricht University, it had a massive stage. I could put Hutchison samples in there. I could put the whole line reactor unadulterated in there and look at parts of it. With Allen's one, it takes smaller samples, but it can still take things that are 3 or 4 centimeters across. The one that I'm looking at is made. It's a field emission microscope, and it's made by Fisher. Is it Fisher? Give me 1 second. I'll find it. And I have a quotation for the device that I want, and by using field emission, it allows for you to put samples in there without having to coat them with gold. Sorry, non-conducting samples, for instance, ceramics that I have a lot of that I can't really properly test without destroying them, by coating them with gold or palladium or silver in a vacuum sort of sputter coater. You put this, you can put it in there, and it uses a low charging process where you can actually analyze the elements in normal non-conductive material. So I can leave those things not undamaged and still analyze what's in there. And it's about 120,000 euros for that to be delivered plus tax. So that is the headache that's there. And I don't care even if there was a sponsor out there that could. It remained in their possession, and I just hosted it. And they also have a means by which you can lease it. So I don't know what those terms are, because I didn't go into it. They just told me to go and speak to the leasing company, and because the company that is the C.I.C. that runs the MFMP, it doesn't have the long track record of earning millions of dollars. You wouldn't get that lease, but it would be a process that would be fruitless. They'd be happy to take your money for the whole lot, but I don't think they would be happy to put the lease. But if someone was in a position where they could prove that they could pay for the lease, the lease might be a subunit of that 20,000 a year, and they even have an option where it's a lease to buy, where you can lease for a number of years. It costs you more than the unit on its own. They also have an option where you can have a lease with automatic upgrade. So basically, it's kind of like a car hire process where you're basically renting off the car manufacturer, and after a number of years, if there's a bigger improvement in the product, you can actually just continue with that payment and so on. So there's many ways to do this, but the unit that would give a significant technological advantage both in optical resolution, scanning electron microscopy resolution, and ability to test non-conductive samples is the Fisher. I think it's thermoscientific unit, and it is, if I got it here, thermoscientific. And the thing is, when you order these things, they take a couple of months to come in, so it doesn't happen immediately. Okay, so it's anyway. It's a thermoscientific one, Thermo Fisher Scientific. Yeah, so I wasn't too far wrong. Yeah, it's called a Phenom Pharos G2, I think it is, maybe SEM. It's a field effect generation SEM. So that is the kind of one that would allow a step change, and then we would be able to do what we do in the US. So Alan, we have an agreement that if people are open about their data, they can do analysis basically at cost, or if it's inside the MFMP, it's essentially free, and we cover it with people's donations. But it's about throughput, and it took from the first time I visited the SciTech up the road here, it was about 5 or 6 years ago. Then they got the money, which in part came from because our project replicated the work of Francesco Celani. They got the money as part of the European funding program, and then it took a further more than 1 bit year to get a couple of sessions on the SEM up there, and then I kind of had to have someone there and saying we can't put that sample in there because it's too big, or we have to leave now because the next person that's booked the unit is coming in, and it's like ugh! And I would have spent a lot of time in America over the last 2 years, but I still can't go because they still have this requirement for you to have something in your body which is completely useless, and I don't need. Anyway, that's enough about that. I'm going to show you the pictures of the device. Okay, so where are we? Give me a second. Okay. So I think what I'll do is I will show try and have two pictures up. So one, the image of the device, and another one showing. Okay, so we'll do that like that, and then we'll do this like so. Okay. Okay. Right. Okay, so is that going to work? Not really. Okay, well, we'll just do it like that then. Okay. Okay, so here is the schematic that Dave drew. He says, it's not going to be perfect. I said, it doesn't really matter if it's perfect. It doesn't matter if it has all of the details. It's better to have something than nothing. Okay, so thank you very much, Dave Bouclier, for doing this for me. Okay, so so in the center here we have the electrolyzer system, and there is a 1mm titanium sheet either side on which we have placed a 40 kilohertz 50 watt ultrasonic transducer horn. Now, it isn't perfectly coupled, it won't be resonant. The whole structure here has got several different materials in it which will affect its resonance and stuff, but the idea is to introduce some controllable level of intensity and to a certain degree frequency of sound in here to do tests. And then we have 0.5mm pure nickel sheets here, and a lot of this was bought off AliExpress or other online suppliers. Here, I think it's 2mm nitrile gaskets. So you've got 0.5 millimeter, 2mm gasket, 0.5 millimeter of nickel, 2mm gasket, 0.5 millimeter, so forth. So this ends up being a block, which you will see. And you can imagine if the sound is coming out here, there's a sound propagation speed in the titanium, and then there's a sound propagation speed in the electrolyte, which is potassium hydroxide. Again, we suggested we use potassium hydroxide so that we weren't having any carbon in our electrolyte. So that could remove the question of carbon being in the gas that was exposed to whatever the sample was from the source, from the electrolyte, and light water. And then it's going through titanium, then electrolytically, water with electrolyte, potassium hydroxide. Then it's going through these nickel and so forth. So you've got different sound propagation speeds. And so that this, and with the gaskets, that will damp the sound and change the overall response. However, I believe because it's fairly fault tolerant, these kind of sound systems where you have at least some flexibility in the plates, there will be some sort of resonant structures on there. And I guess that once this has been run for a while, we need to do a tear down and a optical analysis of that to find out whether that's actually taken place. Okay, so up here it's got a 24 volt DC 15 amp power supply, and this goes through a pulse width modulator chopper, and this is to adjust the applied power. Maybe he's got adjust current here as well, so maybe he's got some current control on there as well. And again, if David's in the chat, which I don't think he is, that would be great. But anyway, he has a, I think that says 7 amp auto transformer. 0 to 135 volts, 130 volts AC. Okay, and he has 60 hertz, 120 volts AC going in. So maybe it's only 0 to 120 volts, possibly. And is approximately 200 VA transformer here, going to approximately 80 volts AC, which is going to an ultrasonic inverter with variable frequency with a 50% duty cycle square wave, and then that is going into a hand-wound toroidal ferrite impedance transformer. So it's going in there, and then you've got your piece of ferrite, and then you've got your takeoffs here, and they are feeding the two ultrasonic horns. And then he's got grounding on the plates of the titanium here, and then he has the nickel, how should we put it, electrode plates in there. And so that's it. Your ultrasonic drivers are glued to titanium outer plates with epoxy, so that's how that's bound to there. Electrolyzer is sandwiched together with 1/4 inch thick acrylic plastic. Okay, so you're going to see that in the photos here, the acrylic plastic. Frequency set at, thank you very much, Dave, 369 hertz. Pulse width modulation adjust for current control. Okay, so that is the basic schematic that we see there. I hope everyone saw that. Maybe if I take my mugshot off and people can look at this later, I'll just go around it again. This is the power supply for the electrolysis. This is the power supply and control for this is the power supply and the ultrasonic control for the ferrite impedance transformer, which is then feeding the ultrasonic horns, and these are the details on the ultrasonic drivers, so people can piece that together. But the image will be shared on the blog anyway. Okay, and I think what we're going to have to do, and I've said this to Dave and Alan, we need to be writing papers of this so that we can present the papers as part of our next attempt at the Fixing Fukushima proposal. Okay, so what you're looking at here is the schematic. What does it look like in the flesh? It looks like, as Dave would describe, a complete mess. But it doesn't matter. This is what a prototype can look like. And I kind of like the fact that, you know, he's got his power coming in here for the toroidal ferrite transformer over here. And if you go in, it's going in, and then we have like, I think it's 4-core wire coming out of these plus and minus here, and it's going round. And then he's taking, as you can see, you've got yellow, red going to one of the ultrasonic devices, and then you've got green and black going to the other ultrasonic device here, and you can see how this is fed in there into the so like 4-core wire that he's put in there, so you can see how it's actually implemented. And then this is the bubbler, so sorry, this is maybe the pump. I think he's using a fish tank pump, or anyway, it's got a bubbler involved, and you can see he makes judicious use of these food containers with their silicon seals. So what I like about David's work is it's not like always having to buy conflat flanges at thousands and thousands of pounds. He's thinking, how can I get something that does the job that I want it to do, and it's using either scrap or material that's readily available off online sources. And you know, all things that you will recognize if you're into doing these type of experiments. Okay, so I think this maybe is part of the controller down here, and so forth. But we'll get these labeled up again. Like I say, it's quite raw. Okay, so you can see the power delivery to one of the PZT transformers here, and there's another close up here. And so this is the major electrolyzer unit here, and you can see the nitrile gaskets here between the nickel plates and the PZT horn, the ultrasonic horn attached to the outside. Okay, so that's it. Thank you, Diodon. Thank you. Okay, so right, that's it. So I'm going to now look at the titanium analysis, and I think this is very interesting for another thing that seems to have been replicated. And then I'm going to cross-correlate some of the things that have been observed over the last couple of years with what I found earlier today, actually in the document that we're going to look at a bit more later next week, which I found just over a week ago. Which looks into the history of ball lightning, and it's just wonderful how you know, when the data is real and it keeps repeating itself, there must be a story that's based on reality. And when you find that reality has literally centuries in some instances of corroborating evidence that you never knew was there, and it's specifically for ball lightning, then you've got to start saying that maybe there's something that's worth considering here, and we're not just completely bonkers, although we might be completely bonkers because we're doing the work. Oh dear. Okay, so is this okay? Make sure I have both of the papers up here, so just bear with me a second. And this one, I think, go on. Right. So again, I'm going to start off with the stuff from analysis of the experiment with titanium plus fluorine. Bearing in mind the fluorine's there, but there's a specific feature on there that we established through the discovery of the work of Solin post doing that experiment, could be the result of explosive cold fusion, coherent nuclear transmutation. So this was the experiment that you may or may not be aware of. Okay, that's it. Okay, so that was a Ohmasa gas on this pure titanium sheet, and then it was contacted with some PTFE, polytetrafluoroethylene, that's fluorine and carbon as a polymer, and it produced this structure here, which is, in my view, the equivalent of the explosively produced instant coherent nuclear transmutation products, which Solin said in his 1992 patent is a signature, and that it is formed of microcrystals with open voids. Okay, and here is the structure, and it's bounded, and interestingly, it's bounded by a skin of titanium oxide, but inside here, this material is, and you'll recognize this from the other work, it's carbon, nitrogen, and oxygen, okay, and then your titanium. But also we found in these spikes in this particular sample, there was chromium, and iron, and nickel, which are alpha conjugate nuclei based on the particular structure. So, and this spiky thing, as we've shown, there's a plasmoid here in the center, and it has a direction, and it kind of the vector for the explosion is kind of out in this direction. And if you follow this over here, the spiky sections here are over in this component here. These spiky sections are only in this area. Most of the rest of these open cell microcrystals are do not contain these spiky things. Okay, so this will become relevant when we look at the potential replication done by David Boutlier and analysed by Alan Goldwater at his Magic Sound lab. I did the analysis here also with the Magic Sound device. Okay, so that's this structure. So you can see that maybe there's more of this going on under here, but we don't know. But it's definitely going on here, and it looks like this with colour. And this is some mixture of carbon, nitrogen, oxygen, titanium, and in these spikes also chromium, iron, and nickel. And it looks like this close up. And here are the alpha conjugate nuclei in here. And here is the comment here. A superconducting nuclear condensate is a magnetic liquid metal nuclear fuel that generates energy with the generation of coherent radiation. Under conditions of nuclear phase transformations, in the mass of the initial product and the combination of electromagnetic, gravitational, and nuclear interactions in it. Synthesis of elements from helium-2 ion and other heavy elements, in particular carbon, nitrogen, oxygen, in particular carbon, nitrogen, oxygen, potassium, calcium, sodium, aluminium, magnesium, silicon, and iron. These are all of the elements that we have as our story in this presentation and many since. And if we go back to here, just in this very specific, oh God, where have I gone? Here we have carbon, nitrogen, oxygen, titanium, chromium, iron, nickel. That's the heavier element than iron. Okay, so carbon, nitrogen, oxygen, and so on. Solin pattern also, the physical processes in this substance are similar to those that occur in superfluid, superconducting nuclear plasma neutron stars. It obeys the laws of Bose-Einstein condensation and acts as a classical coherent wave. Therefore, it is detected spontaneously without chemical etching of the nuclear fusion product due to the implementation of coherent ultrafast explosive co-crystallization. It consists of many fragments and dispersed areas in the form of ordered clusters of microcrystals which are separated from each other by voids. Okay, and the interesting thing is that these crystals often are not properly terminated. They end up with just not there. Now, one could argue that it's maybe broken off
But sometimes it just appeared that it was like within the enclosing volume. It just ended up by having none. It just stopped. So it's just truncated by the fact that it was outside of the volume. Okay, so he's saying that this is the process. This is the plasmoid, I believe, that went in and did the business. Went into that central structure, and we went in there. Okay. And that is the 10 yen coin, which is not necessary to discuss today, other than the fact that it produced these subquanta in the side channel, and it produced the subquanta on a side channel of the side channel, which had these spheres that moved around and did their business. Okay, so I think that's all we need from that particular presentation. And I will go and show you the data that we got from the titanium analysis. Give me a second. Okay. So, okay, so this is without ultrasonic addition. Fragment 1. So you can imagine this is a very explosive process, and some things come off. This is the fragment. Is this a spirally structure on here? I don't know. Maybe. And he's got some samples here: 2371, 2373, 2372, 2371. Oh, maybe that's a different number over there. And 2370. Okay, so okay, great. Diodon has said he's building the electrolyzer now. That's fantastic, brilliant. It would be great to have a replication as soon as possible. Okay, what we'll try and do, I've asked Dave for a bill of materials, and he says, well, some of this stuff I had lying around, like the old ferrite core and so on, but there are things that can be replaced. But I think the key components are the source of the titanium, the source of the nickel, the source of the electrolyte, and so on, so that it can be properly replicated and that others can verify the findings. Okay, so having a look around this, in this main area, you have on here titanium, carbon, and oxygen, a little bit of fluorine. Again, this is not there. I don't know why that's there, but it's well below 1. Titanium, carbon, and oxygen. Again, it's more of the same story. If we go down here, this is looking at sample points. So this is no ultrasonics. But there was a fragment, okay? And in that fragment, it was, if you look at 2380, 2879, and 2381. Let's do 2380. What's 2380? 2380 is titanium, carbon, and oxygen. And 2379, titanium, carbon, and oxygen. And 2381 is titanium, carbon, and oxygen. But in this fragment that came out, when you look at this structure, which looks a little bit familiar here, 2332, we see that it has nitrogen in there. And what are we actually looking at? Well, we are looking at something that looks a little bit like open microcrystals. Why do I say open microcrystals? Well, this is 200 microns long. Okay, 200 microns long, about that length. And these are definitely therefore microcrystals. And what do they have? Remember what we were saying earlier. Carbon, nitrogen, oxygen. Carbon, nitrogen, oxygen. Titanium. Oh, we got a bit of iron in there. Where did that come from? Carbon, nitrogen, oxygen. Which one's got the iron in? That's 2383. 2383. 2383. Okay, it's up here. So that's actually on the boundary. Okay, so that to me, this skin here, this skin might be the double layer of the blob or whatever. Is this multiple blobs? I don't know. But this is, it's a blobby blob. It's like a puffed up blob or something. It's almost like you can imagine that, was it a gas that formed in between these structures? How does this form? How does it form? and it has this skin just like we saw in here. And I don't actually have that image, do I? In this one I do if I go to the video. If I go to the video, let me see if I can get there. And go to there. Okay, not the best here, but I've got better images of this. There's this skin. There's this skin here with our microcrystals in there. And here's our explosion and the path out, and it's over here where the highest density of the microcrystals are, and the sort of headwind of that. Actually, these structures here, these are mostly carbon blobs in this area of the titanium, nitrogen, and oxygen microcrystals. Okay, so it has this here. There's the skin. This is the white titanium oxide. TiO2 is white. It's you'll find this in dental products and as if fillers into plastic to make it look really white. Okay, so I'm going to go back to where I was here, and we are looking at our little nugget, our fragment of titanium, and this actually had ultrasonics in it. So this, I don't believe the first lot had ultrasonics in it. They were largely much less no, this had ultrasonics as well. So this had ultrasonics, yes. So down here we have this fragment. So I imagine that when this was occurring, this blew off and this structure was formed, and it has carbon, nitrogen, oxygen in it, and you can see here, and some iron and some sodium here in this part here. Where was that? That was 2387 over here. So on this part of the microcrystal, and it is micro, we're looking at one part, even that part of this dendritic structure, even that part is 20 microns long. This is definitely a micro crystal structure. Again, look here, this is 2393. Now, bearing in mind, we had nitrogen in the air. Okay, so nitrogen could be captured from the air, but could it have come about in another way? Because we've seen other systems where there isn't significant nitrogen, but you see nitrogen incorporated into the core structures. And the CNO cycle is a thing, you know. You start with carbon-12 and you continually add protons, and you go CNO back to C, CNO back to C. And what you do is you produce helium. Well, could the helium production be what causes all of these open voids within this little nugget? Yeah, and it inflates because it's, you know, it's bubbles. It's like a load of bubbles, and this could be a cluster of EVOs, you know, a cluster of microball lightnings. They do aggregate. You can see these clusters of microball lightnings or itonic clusters in the work of Matsumoto. There's literally, it's like a bead, but if you look at the bead itself, it's made up of little structures that are clustered together. And could that be what's going on here? They're like all magnetically bound together, and they have a surface tension. Remember, I showed you that 2001 paper, the Japanese plasma physics paper, where the surface tension was discussed, where these things can wet together, which we've demonstrated in both Dave and Henk's Vega experiments. And so this is the surface tension wetting these things together. We've seen the surface tension in the Vega image here. You've got, let's say, one ball lightning here, one ball lightning here, and if I can get my arm moving in the right direction, one ball lightning here, but you've got the radius around this area, okay? But then you have the surface tension wetting these two together. So that's what I'm talking about here. There is a surface tension between these various parts of the overall macro blob. and the nuclear reaction is occurring inside, and this leads to the form of a coherent nuclear condensate. And when this concludes, it produces an ordered cluster of microcrystals. And we know that alpha is involved because we see alpha conjugate nuclei. We saw alpha conjugate nuclei in this, the one by Ohmasa gas, both on the titanium alpha conjugate nuclei through chromium, iron, and nickel, and on the fluorine through fluorine, sodium, aluminium, so forth. Okay, so yeah, we're seeing more of the same here. Okay, that's back to where we were there. Let's go down. Let's go down. Carbon, nitrogen, oxygen, and here is a map of the thing. So obviously you've got titanium everywhere, nitrogen, oxygen. Okay, and then Alan went and had a look at some closer fragments on there. So he didn't find any whiskers in this particular sample. And so that's just what the case is in this particular sample. Okay, so you've got nitrogen here. Okay, so varying in nitrogen content here, up to 11% in that one. Now, I think we need to do some analysis of the ratio of titanium reduction compared to the carbon, nitrogen, oxygen observed in various fragments of this overall structure. Same story pretty much everywhere. You can kind of see the substructure going on here. Look, you've got hexagons. These have lines coming out, and then there's almost like a truncated hexagon in the center there. And what is this structure? What is it? I don't know. What is this structure? I don't know. What is it over here? Are we looking at something similar? Okay, so that is that, and so Alan Goldwater sent me a document that showed that this company using a magnetron, which is a microwave device, sputtering device. Now we know the microwaves can do transmutation of matter. He showed the production of nano gold dendritic structures, and I'm going to dig that paper up now. And then these were grown on a titanium oxide, titanium nitride surface. Okay, this was Alan doing some due diligence, trying to find some paper that had some structure somewhere on the internet that looked a bit like this thing that we'd now replicated across Ohmasa gas with titanium and the ultrasonically stimulated HHO generator. That we've worked on, that David Boutelier had produced. Okay, so let me find that. It's here. Okay. So here it is, novel gold dendritic nanoforests combined with titanium nitride for visible light enhanced chemical degradation. So this is the paper from 2018, and you can see here these structures, and if we click on them, at first glance they look similar until you find out this is the titanium nitride surface, and what you are looking at is these structures, and they are dendritic, it's true, and dendrites grow wherever crystals form, but this is being produced in a magnetron driven plasma situation. So, and where is it? Here, there's another shot here. But what we can say is, firstly, they're not straight. Secondly, they're gold dendritic structures with titanium nitride on them. And then look at the scale here. The thickness of this entire layer is 1 micrometer. Right? The actual structures, they are nano dendritic structures, and these are grown in a sputtering device, okay, in a magnetron device here. So in this study, gold dendritic nanoforests slash titanium nitride tin composite was firstly proposed for visible light photodegradation of pollutants. A high power impulse magnetron sputtering system was used to coat titanium nitride films on silicon wafers. So I guess this is a silicon wafer with a titanium nitride film. And a fluoride-assisted so we've got fluorine in here, galvanic replacement reaction was applied to deposit gold dendritic nanoforests on the titanium nitride silicon substrates. Scanning electron microscopy images and X-ray diffraction patterns of titanium nitride silicon and gold dendritic nanoforests silicon samples verified the synthesis process was accurately controlled, the average reflectance of so on. Anyway, so it's possible that these structures can be made with a different process, but it's not at the what I would call micrometric scale. These are really at a much finer scale than the ones that were instantaneously produced with the HHO or the Ohmasa gas and titanium in air. So I passed comment on that with Alan, and I'm going to give you my comments here. Okay, and I'll put this in a more sensible way in the blog. And in fact, I misinterpreted its formation when I wrote this to Alan. I said, indeed, that fragment has an open cell dendritic structure with similar basic composition of titanium, oxygen, nitrogen, as we observed in the case of Ohmasa gas and titanium versus PTFE, where you have hydrogen plus oxygen plus titanium and carbon plus fluorine in air, oxygen plus nitrogen. As you can see from the attached PDF, surface areas outside the main blast is titanium oxide. So this is when I'm talking about okay, this is when I'm talking about our experiment. As you move close to the blast areas, carbon starts to appear, and then, so what am I talking about here? This might be a messy. Sample 188, is it? No, it's not that one. Give me a sec. No. Yes. No. Give me a sec. Okay, so how can I get these both up? Maybe I can do it like this. This might be a bit technical, this next bit. Oh, sorry. Not that one. Okay, I think we're there. Hopefully this will make sense. Okay, here we go. So, as you can see from the attached PDF, the surface area outside the main blast is titanium oxide. Sample 188, page 1, 193. So 193 is 19. Okay, so there's an area here. Sample 193 up here in the top right-hand corner. You can see our Ohmasa gas versus titanium dendritic structure here, and it's encapsulated titanium oxide structure here. So sample 193, this is the main blast area, this is the sort of shock wave area, and this is out into the flatlands, the sort of barely touched sample over here. And when you look at that, it is TiO2. It's tungsten oxide. Okay, so that's sample 193. So that's my point I'm making there. As you move close to the blast area, carbon starts to appear. This is 192. So we're going to go back to here, and I'm going to go to 192 here, 192. So carbon starts to appear in 192 here. So it's still mostly TiO2, but there's a start of carbon appearing as we approach closer to the effect area. The only place you see near pure titanium is on the free space nucleation point on page 5. So there we go. Sample 202 is down here. So this is nearly pure titanium here, and it's the free space nucleation point. So here you see nearly pure titanium. Okay, no oxygen, no nitrogen, just a very, very small amount of carbon here, and so I call this the free nucleation point. There's another one here. Okay. The dendritic open cell dendritic crystals have nitrogen in them in both Ohmasa gas and Dave's cases. Nitrogen is in air. However, there is no iron in either case reactors. The reactor has no iron. There's nickel in Dave's reactor, and there's titanium actually in Dave's reactor. Then there's water, and there's potassium hydroxide. So there's no iron in the actual thing that actually is producing the gas, is what I'm saying there. Now look on page 7, where you have the highest concentration of nitrogen. So on page 7, you've got the highest concentration of nitrogen. Okay, so here, this is what I'm referring to there. So this is all for the Ohmasa gas versus titanium. So you've got the highest level of nitrogen here. One wonders if it is a fission fusion of titanium, which was observed by Arroytsev in the explosion of titanium foil underwater, no nitrogen present. I argued in my Acc presentation that Arroytsev was making and igniting HHO in the presentation. So we're going to go back to Arroytsev, which I talked about earlier, and his work is here. Okay, so in this work by Arroytsev, he started with titanium in water, and he was transmuting mostly the most abundant isotope of titanium. Almost all titanium is 48, and he was producing, drum roll, sodium, magnesium, aluminium, silicon, potassium, calcium, vanadium, chromium, iron, nickel, copper and zinc. And in fact, in the ball lightning spectrum that occurred above, he also saw copper, zinc, chromium and nickel, calcium and sodium. Okay, so somehow the synthesized material that occurred in the reactor was teleported out, or maybe, as was stated by the work of Matsumoto, it can travel along the wires. And in fact, if you look at this document, which I'm going to give you a little brief look at today, they discuss in many places how ball lightning is able to travel along wires, and so therefore it can transport the material that was synthesized in it. And this was clearly stated by Matsumoto, and I've discussed that paper in the past. Okay, so here we have the elements we see being produced in HHO with titanium that's exploded. Now I believe that he's getting copper and zinc. We observed chromium, iron and nickel, but we didn't observe copper and zinc. And I believe that is because in the intensity that can be achieved using HHO, you basically can't get really beyond nickel, okay? But in the intensity that can be achieved by this intense electrical discharge, exploding the titanium foil in this water, you can go further in your synthesis of heavier elements. So bearing in mind it's titanium and water, and titanium is lighter than vanadium, chromium, iron, nickel, copper, and zinc. So all of these elements are fusion products. They have to be. Titanium is heavier than, well, actually, it's lighter than 22. Yeah. It's all these ones here: sodium, magnesium, aluminium, silicon. Silicon is 28. Yeah, it's 48 here. So calcium, potassium, silicon, aluminium, magnesium, and sodium. These are all lighter elements. So there is fission and fusion. Fission and fusion going on in here, and most of the reaction product that is transmuted is 48. So this gives us something that we can do. When we look at the sample that has been produced by the work of that nugget, when we look at that nugget, if we took that nugget and saw that there was a reduction in 48, and if I go here, I can actually pull up the paper. It's one of the papers, but this is George Loshak's paper regarding this work. You can see this is the experiment here, and the ball lightning occurred above, but this is the titanium 48 ratio. It's gone from being 73% of all of the titanium down to 68%. What I would like to do is to take that nugget, dissolve that and do a ICP-MS, or try and make a lot of those nuggets and then do ICP-MS. And if we see this reduction in isotope 48, then I believe that we are replicating the work of Leonid Aretskev. And why is that important? Because Leonid Aretskev showed fission and fusion, which we've observed in this experiment and was observed in the Ohmasa gas versus titanium plus PTFE experiment. Fission and fusion, okay? Making fusion and breaking fission, okay? So either side of the titanium 48. But he also observed ball lightning, fracturing of ball lightning into subunits, the production of strange radiation, and the production of magnetic monopoles. The whole gamut. Okay, so this would tie this to essentially being the same thing. It is HHO. That's what he was doing. It's just more intense because of the electrical discharge. Okay, and you can see the element synthesis here. Now, what does he see produced most of? He's not looking at carbon and oxygen, and the reason is probably because he was using a technique that doesn't look at those things. So he might have been using XRF, and XRF can't see anything below sodium. Okay, so that might be why he's only seeing sodium. I would suspect that if he was using some other technique to analyze the elements, he would also see a lot of carbon, nitrogen, and oxygen being synthesized. But these are the elements he's looking at, and he sees, what does he see? He sees mostly aluminium, silicon, chromium, and so on. But the iron is the highest proportion of elements synthesized in his case. Why do I believe it's seeing this mostly? Well, I believe he's seeing that mostly because he's got this intensity of his discharge, because he's doing a capacitive discharge in there. Okay. All right. And he goes on about other experiments here. Here's the different ball lightning here. And it's a mirror above, so you're seeing it from straight on and from top down. Okay. And here's the strange radiation tracks. Here's sort of plasmoid wake, comet type wake. And this is looking at the Mossbauer spectrum that came from the so-called magnetic monopoles. Okay. So I then go on and I say, I argued in my C.I.C presentation that Aritskev was making and igniting HHO in his experiment. He mostly saw the disappearance of 48 titanium, which is about 74% of natural titanium, and the three most abundant elements formed were iron, aluminium, and magnesium, all observed during the experiment in Japan. So, where have we got it here? Anyway, not on this particular piece of data. All observed during the experiment in Japan. So you can have fission examples here. So maybe I can zoom into this a little bit more. You can see. Fission examples is 48 titanium goes to 30 silicon plus 18 oxygen. And you have this energy as required. 30 silicon goes to 17 oxygen plus 13 carbon. With this energy required. So you've got fission to silicon, and it's difficult because this process all occurs at once. It doesn't occur like this, but you can see the process that would happen to get the products that you see. We see a lot of oxygen, we see a lot of nitrogen, we see a lot of carbon. 30 silicon, 17 oxygen, 13 C plus it needs a large amount of energy. Or 30 silicon goes to 18 oxygen and 12 carbon. Okay, there is a fission path where you can have titanium breaking down to 2 oxygens plus nitrogen. This does require cold neutrinos. Okay, but as we said, that's possible. So I've just done some decay products here and products here. So I'm therefore then conclude with respect to the work showed by Dave's work. I say I therefore think that this particle, the particle that we're talking about, this dendritic structure, represents explosive coherent nuclear reactions of the type described by Solin in 1992 and achieved now in Ohmasa gas plus titanium and Dave's HHO plus titanium, which are also supporting the hypothesis that Aritskhev's work is HHO. I think the difference in Aritskhov data, synthesis of some extra lighter elements, silicon, potassium, calcium and vanadium, and some extra heavier elements, copper and zinc, could be accounted for by the intensity and instantaneous nature of the capacitive discharge. So if you can imagine, we've made a little maker and breaker, and it can only push the elements either side of the starting element within a certain degree. If you had a little maker and breaker and you had potassium and lead, then when it's mixing those elements up and averaging them, you're going to end up somewhere in the middle. That's why the alchemists like to use these bismuth, these mercury, this lead, and the potassium and the calcium to produce a reasonable chance of getting gold. You don't get all gold, you get some of it, and so on, unless you get the resonance phenomena exactly right, and it can only be the parameter space is so wide. So what I'm saying is that in our experiment and in Dave's experiment, in our analysis, it's going a little bit either side of the titanium. In the work of Aritskev, because it was more intense, it's going much further at either side. And this is equivalent to what happened with ultrasonics, with Leclerc, when he was using either laser cavitation or intense cavitation with the pressure drop through on aluminium. He was getting every element in the periodic table and some elements outside of the stable elements in the periodic table. This is what was happening in the 1/10 of C 300 joule discharge into a metal target of Adamenko. Because it was so much more intense, he was getting every element in the periodic table. But in this work, the Ohmasa gas and the HHO work, I believe this is because it's got plenty of abundant light elements involved in the case of protium, light water, and it's got generally a light element involved. When it's producing these yin-yang structures, the Ohm, the maker and the breaker, it is not pushing the elements too far either side of the starting material. Okay, you're getting some fusion, you're getting some fission, and actually, the fusion, the fission is kind of like a nucleon exchange between hydrogen, protium, and the starting element, tritium. Titanium. You're getting it somewhere in between there. So it can be a nucleon exchange reaction as much as a fission reaction. The fusion reaction tend to be fusion reaction with alpha conjugate nuclei or protium. And I've discussed the mechanisms for that in the past. So further to this, I have a request for you to Alan. Okay, so I just asked so on. And I say, I think that given this, the previous tungsten findings, HHO, Ohmasa gas, brown gas, is Laena in a can, and many so-called Laena systems are HHO in disguise. Okay, so that, I believe, is where we are. David Boutlier, I think maybe there might be excess electricity. Now, I'm just going to show you a couple of excerpts from this Bichkov et al. Piece, because I think this is relevant. And I'm going to see if I can get that very quickly. For those that don't know, Dave Boutlier is in the chat, so you can ask him specific questions with regard to his embodiment. And I'm just going to go through this document, a couple of items here from this ball lightning investigations. It's 173 pages long, but we're only going to touch on a few points that I think are relevant to what we are discussing here today and have seen in recent years. So, ball lightning investigations, VL Bichkov, A.N. Nikitin, and Henk is going to love this, and I'm probably going to say it wrong. G.C. Dikwi, he's from Holland, and I have tried to reach out to him, and if people go and search his name and what he's done, I think you will be literally blown away by the company he set up. I'm not going to talk about it today. I think I'm just going to leave it out there for people to do their homework. So it's Dijkhuis, and you could not make it up. Anyway, so it starts in. Now starts off by saying modern state on ball lightning investigation. So this is actually from 2010. Now there is a necessity for analysis of rare properties. Theoretical models need to provide an explanation for ball lightning mechanisms of high specific energy content holding of non-compensated electric charge. Okay, the first meeting of scientists investigating atmospheric electricity with ball lightning was held in 1753 by Professor George William Rickman. Professor George William Rickman was killed by its stroke during a thunderstorm. The key document that first really brought ball lightning into people's consciousness, though, was Walter Brand's book, Ball Lightning Publications, in 1923. Brand, in his book, had represented 215 ball lightning observations, descriptions from 1665 to 1919, as described by eyewitnesses, and indicated 14 major features of ball lightning. Now, I'm not going to go into all 14 features, but we will have a look at a couple of them. 1. Ball lightning more often appears at the end of thunderstorms. Feature 6. In the majority of cases, the form of ball lightning is spherical. Sometimes it is hollow, sphere, and sometimes it is compared with a soap bubble. Okay. The average diameter of ball lightning is 20 centimeters, and its size ranges from 1 to 2 centimeters to 27 meters. During its lifetime, ball lightning size can be constant, increasing, or decreasing. In a number of cases, ball lightning is rotating or rolled over the ground. The major colors of ball lightning are white, white, blue, dark blue, yellow, green, yellow, red, and red. And the last one appears to me more often than others. A change in the color of the ball usually takes place before an explosion of the ball. It becomes white from red-yellow. The ball being yellow before an explosion becomes red-blue, and the white central part of the ball becomes red before an explosion. This is 1923 from a study done in 1919. There are reports of observations of black ball lightning, as if consisting of dense smoke. Sometimes ball lightning leaves a smoky trace behind itself or is covered by smoke or vapor. Observers usually compare the smell of smoke with those of burning sulfur or burning powder. They generally describe the vapor as being the orange gas that can be identified as nitrous oxide, N2O. Here we have nitrogen and oxygen. Is it capturing it? Is it synthesizing it? Who knows? In other cases, the smell was identified as the smell of ozone, especially when ball lightning was observed by people belonging to science. In most cases, there are no material traces after ball lightning explosion. In the vast majority of cases where observers were at a close distance to ball lightning or have touched it, they point out the absence of the feeling of heat from the heat emitted from it. The effects with heat release most often take place during ball lightning explosions. Okay, the effects of... So, what is heat? Is it a kinetic conversion of particle movement into thermal vibrations when a ball lightning explodes? But what he's saying there from 1919 study done over anecdotes from hundreds of years and published in 1923 is that those that are close to ball lightning don't observe much heat from it. And this is what we see in those samples from Henk when it is taken out a spherical structure from copper. It's what we saw when we exposed Ohmasa gas onto the 10 yen coin in Japan. It cut out copper mostly, a little bit of tin in there in that 10 yen coin, very little tin. Mostly a very, very thermally conductive material. It cut it like a laser. What it is suggesting is that within that boundary, that event horizon, it does everything. Outside, it doesn't. We've seen this over and over and over again in Vega experiments, most notably in the way that it cut tungsten wire, and most specifically the spherical structure caught in the cylindrical section of a copper plumbing pipe, where it cut out in multiple axes, the hemispherical structure of a ball lightning that was bound to the magnetic iron substrate that it was on, and it had this clean cut line in multiple axes. So this fits with the 1929 summary of this review of ball lightning observations. Okay. Ball lightning at close contact with an observer's body can cause temporary loss of consciousness. Well, isn't that a thing? Well, maybe you could say it's a bit like a stun gun. Paralysis or even death. There are many cases of animal deaths during a ball lightning explosion. Why? Well, if you had lots of coherent matter suddenly exploding, releasing non-thermal electrons, which have got Coulombic repulsion movement, but they have no thermal energy. There's a range of processes that occur, and if they're coming out at keV kind of kinetic speeds, then there's a lot of damage that can be done by that Coulombic explosion. Okay. There are data about mechanical work executed by ball lightning, stone spreading, transportation of people, and I'm going to zoom this in because I think it's quite fun. Transportation of people and animals in space by ball lightning, and making holes in thick walls, wooden doors, or window glasses. Ball lightning is capable of making a deep pit or a trench in the ground, throwing a tile from a roof, or swinging a church bell. It can evaporate wine, oil, and water in earthenware, leaving the vessel safe. Tear a shirt to pieces, instantly melt down a piece of ore or gold. Look at that. Instantly melt down. Melt? Is it really melted? Is it really melted? Or did it just become a liquid? Down a piece of ore or gold and tear away a ring from a finger. Tear away a ring from a finger. Could it make non-metallic items magnetic and then pull them into itself? I don't know. Maybe. Ball lightning can impact electrical devices, cause glowing of bulbs. Its explosion is accompanied by melting down of safety fuses and burnout of light bulbs. This would imply, electromotive force, an EMP. Sometimes ball lightning is a sound source. Probably one can connect ball lightning sound with electric charge loss. Sometimes ball lightning reaches the Earth's surface, but sometimes ball lightning fall is stopped at a height of 1 to 15 meters, and ball lightning starts moving horizontally. It's kind of like what strange radiation does. Ball lightning's path is never straight. Okay, I missed that last bit. Nope. Okay. Where are we? Down there. I've done that one. And I'm down here. The features of ball lightning motion can be explained by its attraction to metallic objects. It's attracted to metallic objects, and its tendency to move through chimneys can be associated with the electrical conductivity of smoke. The path of ball lightning motion in some cases remains along the electric conductors. It moves along the telephone, telegraph, and electric cables, wires of lightning rod groundings, drain pipes, and tree trunks. So remember what I said. This group in the Soviet era developed a Tesla-based spark discharge method of transferring large amounts of energy along an 8-micron wire and lighting 40 kilowatts. I think it was 25 or 40 kilowatts. Definitely 25, obviously. 25 kilowatts of tungsten filament light bulbs. Okay, so what we are seeing is a pattern where Matsumoto is saying, post this Soviet work of transferring this vast amounts of energy, reported in 1992 by Tom Bearden, sadly departed Tom Bearden, where they were transferring vast amounts of energy along a wire. Matsumoto called this a new form of electrical current, and he saw the transfer of a large amount of energy along the wire and the deposition of carbon that was either synthesized or captured at the end of the wire. And here you are seeing from 1929, they are stating what it is, that these ball lightning can transmit themselves down wires. And that is what you saw with Leonid Orytskev. The ball lightning is formed by the HHO in the exploding titanium foil, and then it travels along the wires out and then forms outside of the chamber. Okay? It's not so much teleporting as it's passing along, it's using the wire as a guide and then forming in the air outside, presenting the elements that were synthesized in the process inside as the ball lightning falls apart in the spectrum of the light emitted. Okay. So 1929, we're really pushing the understanding of what we've witnessed since, and people think they're rediscovering it, all the way back to that survey done in 1919. Ball lightning can penetrate through keyholes, slits and cracks. In rare cases it can penetrate through glass, leaving it intact. Sometimes it makes a fist-sized orifice. In many cases, ball lightning's life ends with an explosion. Sometimes an explosion sound is described as a gunshot or rifle shot. The explosion is often accompanied by a bright light flash. Oh, really? Really? Like what would happen if a lot of ions, which had no electrons, had to regain their electrons to reconstitute the atoms. A bit like that. Could it be a bit like that? I don't know, maybe. 1919 survey. Hundreds of years of testimony, published in 1923. Bright light flash, just like we saw in Evo Blaster. Thank you, Henk. Lightning and pieces of matter and sparks flying out of ball lightning. Sparks flying out of ball lightning. I wonder if you could slow those sparks down. Would they look like strange radiation tracks? Maybe they would. Could that be the collapsing of the coherent matter, yin-yang wetted together surface tension structure? Oh, possibly. Sometimes ball lightning divides into several separate balls. Yes, 1923. That is exactly what was observed by Orytskev in 2001. Separate balls that either continue their existence or go out. We observed it, transmuting the oxygen on the 10 yen coin into sulfur. Ball lightning division can take place in the air and at collision with some objects. Balls of smaller size practically do not differ from the initial ball. Balls of smaller size. So, on the 10 yen coin, we saw the main structure that had the yin-yang. It ate out one side of the eddy current, the overall structure. Off to one side, we had one at 90 degrees, orthogonal to it, same structure on the side. On one side of that, we had the little balls. Self-similar, as above, so below. There are rare cases of ball lightning pairs located one over the other and connected by a thread. One over the other, connected by a thread. Where have we seen that before? Bearing in mind, I read this afternoon, and this is what we are seeing in multiple circumstances, which I talked about in the last presentation 2 weeks ago. Pairs located one over the other. I would suggest that is one over the other, a bit like that.
with a thread that links them together. What could that thread be? What could it be? Ooh, could that be the magnetic flux loop? I think it is. Okay. Natural tissues, cotton and cloth, become fragile or tear to pieces after coming into contact with ball lightning. However, traces of burns left on the tissue disappear after washing. Well, could the burns be carbonization? Could it want the oxygen in that material so much so that it burns it? But it's only a very light surface effect. I don't know. Anyway, tinted tissue becomes colorless after coming into contact with ball lightning. Well, that's what would happen if you are bleaching something, if you are oxidizing it. So maybe the nitrous oxide, not that, but maybe the ozone. Maybe the ozone is bleaching the tinted tissue. And this potentially gives us ways and means by which we can actually look for microball lightning traveling by actually using tinted tissue and seeing if it changes it. In the work of Leclerc, he actually saw a triangular blackened pit on paper, and this would be one of these burns caused by, in his view, a water crystal traveling out and interacting with the paper. But in this work, which is from 1923, they're saying it's ball lightning, which can be of all scales, from like extremely small, micro, all the way up to 27 meters in his work. In certain cases, there was a series of concentric wave patterns around a circular hole. Concentric wave patterns. Okay, what you mean like we saw on the calcium carbonate that was formed into calcium oxide and then had silver on these concentric wave patterns that were observed by Solin. But this is in 1923. It's in 1923. Oh, God. Okay, where did I get to? This is what happens when I'm zoomed in. Okay. Got to there. Did all that. Okay. There are rare cases of ball lightning pairs. Okay, so blah, blah, blah. Okay. An electrical discharge had occurred between ball lightning and the grounded electrical wire when ball lightning came into contact with. This caused melting of the wires. Okay. So in this example here, they're talking about the fact that a large orange fruit-sized red-coloured ball lightning had fallen into a tub, and this was the case where it seemed to boil the water off for several minutes, and they calculated it was 3 times 10 to the 10 joules per meter cubed, the volume. 10 megajoules was actually created. I have argued that this is because you don't get any heat from these things, but when they go in, matter is pulled into the coherent matter layer. It then gets incorporated into it. It has to condense. It releases very localized heat, or rather light, intense light, that then potentially could dissociate the water, which would look like boiling, or partially heat it, because there's thermal energy that might get released, but in the form of light that needs to then down convert. So anyway, for whatever reason, it appeared as if this was boiling. So this, I didn't realize that this testimony, which I think I heard from, I actually heard this first, and I've talked about it a number of times. I heard this from Dr. George Eagley when I was in India in 2017, but actually this case has come from this book by Brand in 1923. That's the provenance of this particular case. And there's another one here, Lomonosov thought. So this is in 1965 in the USSR, popular scientific book of Leonov titled Ball Lightning Enigma was published, 53,000 printed, blah blah blah.
so this Professor Richmond's death investigated by Lomonosov. Lomonosov thought that ball lightning could come into the house through an open window, a room adjoining a room, blah, 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 blah. A clock stopped in the room with the open window. This is the key point here. There was also a report about the appearance of walnut-sized bright red ball from the heating of a Russian stove. The ball had flown over a bag with surgeon tools and subsequently flew out of the hut. It was determined that metallic tools in the bag became magnetized. However, their magnetization had disappeared after a day. On the basis of this observation, one can make a supposition about one more feature of ball lightning. Ball lightning can magnetize steel, i.e. non-magnetic objects close to them. Apparently, this ball lightning feature is presumed to have caused the stopping of the clock observed by Lomonosov. Why is this interesting? Well, obviously, John Hutchison observed magnetization of metals, but that seemed to be more permanent. I think that's because if you get steel and you reorganize the elements in there that these, in my view, yin-yang structures, these monopole structures do, you can end up with pure iron in places that the actual magnetization of the structure causes to become magnetized. Okay, if it's other elements that are transmuting to iron, then that will occur as well, as we saw in the coral twist sample. In these phallico-soliton structures, there was actually iron synthesized and other potentially magnetic elements synthesized in the cores of those structures. So it can actually become magnetic elements, and the magnetic flux loop will then magnetize them. In his case, they're talking about the temporary magnetization causing the stopping of a clock and some steel tools which should not be magnetic becoming temporarily magnetized. And we saw something similar with our copper constantan wires changing their magnetic states, and also Matsumoto observed changing in magnetization properties. Now, we know from Oretskev work that these structures come out that are able to change the magnetic constant of the iron 57 sample, and if these are magnetic, they can go into paramagnetic materials and then build up a certain magnetic state in those. And I've argued that the reason why Hutchison samples jiggle about, if they're kind of like a paramagnetic material, or if they're something like iron, they just stay there and then they break, is because you have these magnetic monopoles building and building and building until the yield strength of the metal is surpassed, and the metal just falls apart, because it falls apart, and it just falls apart just a bit because the fall off on these structures is so small that it doesn't need to go far apart before it's then in a new stable state. And so, and I believe that the remaining material that gets left. So he had, for instance, a wrench, and the wrench had north-south, north-south. So there's a combination of effects goes on. You had a piece of steel. It then becomes, these magnetic monopoles are reorganizing the matter. So there's a phase change. So some of the steel element becomes mild steel in terms of can become magnetic. The monopoles then push the material apart, and so you get residual. You get north-north facing each other, where the bits would go together, but they don't go together anymore. And so you get the combination of both effects. But I believe what's happening here is that over a period of time, that the monopoles can maybe dissipate in certain materials, and therefore the state of magnetism drops down. And it might be that parts of the actual ball lightning that itself is magnetized get left with the metal that they come close to, and that isn't actually changing the metal so much as just on the surface. And in Bogdanovich's work, where he's firing that gamma ray that's being created by the electron beam going through a conversion target, when he's firing that through a magnet, he actually argues in that paper that the monopoles that are being caught on either side of the X-ray film are actually being ripped off the surfaces of the poles of the ordinary magnet, which is used to deflect the electrons. Okay, so he's saying that they aggregate on the poles of a magnet, okay, and that they can be knocked off into clusters, and that is what you see. So when you line this data set up from 1923 with these multiple observations from multiple parties, you start to see and get a grasp of how real this is. And it's just a beautiful thing. It really is a beautiful thing to see the correlation between experiment and what's going on in nature. Okay, so let me see what we can see. See if I've found something interesting. Okay, there's a couple of things that were relevant specifically to the presentation today. So again, this is from 1936, is it? From 1930? No, it's not from 19. This is also from Brand's 1929 paper. And he's saying here, the noise increased in the transistor receiver during the approach. So this can't be then. This can't be then. This must be later. I think this is in 19. I think I've noted it here actually. Noise in a transistor radio. This I think is in the 1960s, maybe. Oh no, a new symbolic event took place in 1971 in the USA. The book of Stanley Singer, titled The Nature of Ball Lightning, was published. After 2 years, its translation into Russian was published. The number of copies of the Russian edition was about 10,000. Okay, so this is 1971. And the ball light, I think this is a ball lightning observation from 1967, I think. Yes, okay. So this is from 1967. And in this particular event, the noise increased in the transistor receiver during the approach of ball lightning, which transformed into a continuous roar. Dmitriev took 4 air samples after the ball from its tail. In the first and the fourth samples taken at the 55th and 70th seconds after the ball lightning flight, the ozone O3 and nitrogen dioxide NO2 concentrations proved to be at level at 0.1 milligrams per meter cubed. But in the second and third samples taken during the 60th and the 65th seconds, the concentration of these gases proved to be 10 times greater. One can formulate 2 more features of ball lightning on the basis of Dmitriev's observations. Ball lightning is a source of radio radiation at frequencies of 0.3 to 3 megahertz. Why is that so cool? That's cool because John Hutchison used an AM radio to listen to a long wave radio to listen to what was going on in his experiments and know when it was in the sweet spot for the effects. You literally have someone using a transistor radio, an AM device radio, a long wave radio, whatever, to listen to the signature of ball lightning at a certain clustering level when it's able to emit its own radio frequency emissions such that you know it's there. And this is from 1967, okay? And this is what we used in Evo Blaster in Evo Blaster, where we had the Coulombic explosions of the Evos, this bright flash with the sound of the explosion and the AM radio tuned between stations creating pops. Thank you, Henk, for doing this work. Okay, ozone and nitrogen dioxide are formed in ball lightning trail with a delay of about 1 minute. So something is holding behind that's actually allowing the formation of ozone and nitrogen dioxide. So obviously when you have an explosive situation like we did with the Ohmasa gas and the titanium and the PTFE, I don't know, but what we are seeing is increasing production of oxygen and nitrogen dioxide. So we have 2 of our components here, oxygen and nitrogen going on. But of course, both of those are in the air. Now, this is for me the money shot. Okay, so this ties John Hutchison's work with his observations and what happened. It's absolutely unequivocal. It is what it is. Ball lightning, microball lightning, coherent nuclear transmutations, all of that. That is what is going on in the Hutchison effect. The way he was detecting whether it was in the sweet spot was already observed in an interaction between ball lightning and a transistor radio already before that work was done. So if you actually care, you can go backwards and go backwards and find that the work has already been done. You just have to pay attention. You just have to read what has already been done. I think Lion sent me a phrase from an interview with Martin Fleischmann, and I'm going to paraphrase here. He says the greatest shame or the greatest tragedy in the field of Laena is that, I think it maybe even in research in general, but I think in the field of Laena is no one bothers to read what someone has already done. Well, I'm doing it for you here now, and I read this afternoon. I was reading the tail end of the document, which we'll talk out about next weekend. But I was reading this afternoon, and I literally couldn't believe it. It's like, yes, we've seen that. Yes, we've seen that. Yes, we've seen that. It's ball lightning. It's a natural phenomenon. You can't fight nature. Nature's doing it. It is real. But here, listen to this. And can melt a metal and surround the molten place with soot. I'll read it again. Can melt. Is it really melting, or is it turning it to a liquid? A metal. Definitely seen a lot of this going on. Definitely that's also what John Hutchison saw. And surround it, the molten place with soot. What is soot? It's carbon. Interaction with metal. It likes metal. It gets into metal. And you see a lot of carbon produced. Carbon is soot. This is from 1967. It's already observed. What was the claim of Yule Brown? That doesn't matter what metal you use, you apply a brown gas to it, and when it flashes, you get certainly he could turn it to a liquid, and he can turn different liquid metals to different and fuse them, like fusing weird stuff with weird stuff. Okay, this is all well documented. But when you have this explosion, the product that you get most of at the end of the day is carbon, and that is what you are seeing here. And what you see coming out of that sphere of lead in that carbon-free experiment of Matsumoto from 1996 is a carbon plume. What you see from the indium exposed to Ohmasa gas by in the experiment that we did in Japan in 2019 is exactly the same structure coming out of a volcano-like structure, just like Matsumoto said in other part of his books. He says that volcanoes, the magma chamber, may actually be a large one of these kind of structures going on. That it comes out in a plume that looks identical, and it's largely of carbon and oxygen and the other elements that we are talking about here. Okay, can melt a metal and surround the molten place with soot. So here it's all done. You know, it's all done. You just have to pay attention. The lowest ratio of ozone to NO2 ratio proved to be close to 0.8 to 1. We might be able to look at this data here and compare it with the ratio of oxygen and nitrogen in the titanium affected by HHO and Ohmasa gas, and see if there's any correlation there. This is a what he calls a myth that ball lightning radiates energy as a heated black body. No, it doesn't. It radiates. He talks about it later, that it basically irradiates in light, which is what we observe. Ball lightning does not reveal a visible magnetic impact at a distance greater than 0.5 meters, right? So this is what I'm saying. I've just made the connection right now here with you. I've made this connection. A ball lightning, which can be big enough to observe, so this is quite a big ball lightning. He says it does not make a magnetic impact at a distance greater than 0.5 meters. This means that it has a very sharp fall off. Okay, so if you have a micro ball lightning forming in a metal, when John Hutchison is listening to that radio and he hears this production going on and the metal falls apart, then I'm saying it has this very tight non-linear fall off, and ball lightning observations would seem to support that. Okay. This is talking about a ball lightning, and it had this this system out in the US, and it was looking for meteorites, but they saw some ball lightning events, and there was this trace, and in the trace it resembled a dash line consisting of 40 bright sections. So this is very similar to the Hessdalen effect. So I hadn't realized that this was already recorded in the 1960s. So this pushes back this macro-sized strange radiation type effect back in atmospheric research back to 1960s. So this equivalent, this is to me the equivalent of strange radiation effect in the macro scale, caused by the same thing, just a bigger version of it. This is a later hypothesis that it was actually gas being produced in the ball lightning, and I actually think that might be going on, although Bitchkov says he doesn't believe that is the case. It's not the predominant mode. Okay, well, here we go. Absence of heat at close contact with ball lightning explosions and sooty spots left by it, separation of object parts, melting and evaporation of melting metals at ball lightning explosion. So here this is just adding icing onto the cake. This is by Stakhanov, and Stakhanov work, I think, where is it? When does Stakhanov came later. I can't remember Stakhanov. I think I note it later on where Stakhanov comes in. In this case, a light flux from ball lightning on average can be compared with that from incandescent lamp of 100 watts. Stakhanov conceded that ball lightning can emit soft ultraviolet radiation, by absorption of which in surrounding air one can explain the observed blue halo. Here we go. UV light coming from ball lightning. It's all the same thing. This again is saying that it's not hot. And then here, oh God, I've gone up one. Is it here? A valuable conclusion about ball lightning features was one that ball lightning substance possesses surface tension. However, he could not indicate a reason for the surface tension existence and proposed to accept it as fact. And this was in 1979. So this is what I'm talking about. I had said that the paper that I'd referred to in the past when we were looking at the surface tension that appeared to be going on in Henk's Vega experiments and later in David Boutlier's, that it clearly had the surface tension, and that the surface tension in this structure that's on the Vega Valley behind me, the earliest discussion of surface tension that I had seen in relation to ball lightning type phenomena was 2001 in the Plasma Physics paper, Japanese journal, and here we have it actually from 1979. That's a lot earlier than 2001. It's also in the same year that John Hutchison first made his discoveries. So here we go, that at the end of his study and the publication of his book in 1979, he had concluded that ball lightning substance possesses surface tension. And this is an absolutely key point here. The presence of the surface tension enables ball lightning substance to create a separate phase in air, different from a gas surrounding it. Most time of its life, a ball lightning has sufficiently clearly defined boundary. A separate phase. This is not solid. This is not liquid. This is not gas. I do not believe this is plasma. I believe this is coherent matter phase. I believe that what this guy concluded, Stakhanov, in 1979 is true, and it has a surface tension, and the separate phase is a coherent matter phase. And probably, as I read through the rest of this document, you're going to find that that is also what is concluded. But I don't know, but I suspect it will be. And you can see I've got to basically the end of my line there. So, essentially what we've done in today's presentation is we have shown that what we observed both in tungsten and Ohmasa gas and titanium and Ohmasa gas is replicated by multiple authors in the past and has been replicated in, I believe, at least an initial look with the work of David Boutlier that we worked on over the last several months and analysed by Alan Goldwater in his Magic Sound lab. The observations of nitrogen and oxygen could be explained by the fission of the titanium in the case of the structures that forms in microcrystals inside a sort of wetted, surface tensioned, bubbly type structure that also contains carbon, and the synthesis of carbon and other elements that were found in tungsten are also potentially from the same process. You have a lot more nucleons to play with tungsten, and so that is why I believe you see many more elements being synthesized from the fission fusion process. When you're starting with titanium, a majority of its isotope is 48. You are seeing elements that are a little bit pushed beyond 48 titanium, and a large number of elements synthesized below that. And all of these effects are intimately related to the nature of ball lightning. And what we've shown in the latter part of this presentation, that beyond the replication of our own work, which replicates the work of many other authors discussed in this presentation and in prior presentations, the observations of ball lightning spanning back to several hundred years and summarized as early as 1923, based on 1910's survey, points to some of the major features. And when you get towards 1960s and late 1970s, the observation of this radio emission from ball lightning becomes a key feature. The observation of UV light coming from it, the observation of a non-linear and short distance magnetic fall off, the ability to influence and in a bizarre way the magnetic properties of materials, the production of carbon from the interaction with metals. These have all been observed since this work on ball lightning was published, but I think it's to Matsumoto's credit, enormous credit, that he recognized that this is micro ball lightning and moved to rationalize the observation of what happened with his experiments to the natural phenomenon of ball lightning. And in that respect, it's clear that also John Hutchison was producing a ball lightning or a micro ball lightning gun in the 1980s. It was in the Electric Spacecraft journal. I've talked about that before on my Hestalin Lights series, and that all these things are related. But what you've learned already in what I've gone through in the little part of this Bitchkov et al. Work is that there are methods, coloured paper, where you can use to potentially detect interactions with microball lightning, but also there is
things like using a radio. And we now have from this 1979 work, a specific frequency range that the radio was tuned to, which could pick up these frequencies that are coming out. And I think it was 0.32, whatever it was. I'm going to type in radio. Yeah, so here, 300 kilohertz to 3 megahertz. This is the range that we can be looking at here. And this for me is, it's just astounding that this was known about ball lightning and independently discovered as a means to establish his effect, John Hutchison, in 1979. And the wetting of the structures, and if we go back to that particle, if I go back to that particle, of analyzed, here is it, where is it? Titanium. If we go back here to this sample, this, for me, is a wetted together cluster. So you have these wetted structures, wetted. This is a 3D structure, I would say, is akin to the structure that was observed by Matsumoto, where you have these balls, these beads, and they have a substructure and they're all kind of glooped together. And that's how this thing would appear if it went splat onto a photographic film, and it was not necessarily at this scale. And then within this overall skinned effect, you have the material doing this crystallization, open cell crystallization going on within this volume. Okay, and I believe that that is akin to what we witnessed here in the Ohmasa gas. If I go back here, and you can see it in the background here, and he says, therefore it is detected spontaneously without chemical etching the nuclear fusion products due to the implementation of coherent ultrafast explosive crystallization. It consists of many fragments and dispersed areas of the form of ordered clusters of microcrystals which are separated from each other by voids. Okay. So I think we have replicated it. I think there's an opportunity to build on this replication. It means that Ohmasa gas is the peak, because we've seen the magnetohydrodynamic structures at several self-similar layers on the 10 yen coin, and separately on the outside of the main area on the tungsten. So what we can learn from that is that some of the most interesting action goes on outside of the area where most of the damage occurs. Okay, you want to look on the periphery. You want to look on where the strange radiation interacts with at a distance. And this is why a witness material that's nice and clean at a distance is better, because things that are close to the action, what you end up with doing is it's kind of like going to a city and trying to work out what happened when the whole thing is bombed. There's probably a bad analogy here, but like where you've had a city there for thousands of years, because people have built things and destroyed things and built things, and then they've taken something down and they've used the building materials from that to build something else, and it's all churned up, and the history's all mixed up. So it takes a lot to unwind the history of that place. Let's say you went to a place where there was one person that built one building on some virgin ground, but the thing was also destroyed for whatever reason. Maybe there was a flood or cataclysm of other kind. You go there and you go, well, this bit fits into this bit and there's no other bits, and these are the only bits that look like they were made by someone who was trying to make something, and you can admit it's much far easier to put together a single event in a single place of otherwise virgin land than it is to deconstruct and reconstruct what happened when the thing has been mashed up. And so this is why I think probably my advice coming from this and what we've seen today in these various things is don't go and look at where most of the action occurred, because it's not going to tell you a story. Look around the edges. Look at the peripheral. Use a remote view on it. Not view in the center. Have a remote view, remote from the main action, and see what happened as Roitskev observed. The big ball lightning breaks up and forms these little ones. You want to find out what the little ones did. And I think this is the insight that Matsumoto must have had, because he had his action going on, but he then used these witness materials, which were even single crystals or in some cases, but he would have like these virgin pieces of polished metal that were at a distance that would receive whatever was going on, and then he could identify things separate from each other. That is what you need to do. You don't necessarily need to run an experiment for a long period of time. It's like the ultra experiments. When we run an ultra experiment for 90 seconds or 200 seconds or whatever, you can actually see more of what happened than if you run it for like 10 minutes. Because if you run it for 10 minutes, basically you've got no aluminium foil left, and you've got something happening on something else and happening on something else. So the story here is, some people have obviously thought we need to run an experiment for a long time to learn something about it. No, I'm saying let's run it for a really short period of time and do multiple short experiments. And that's kind of where I think we need to be here. Okay, so I'm going to look through your comments here. If people would comment both in the YouTube recording, but I prefer over at remote view because I can give proper replies to that. Okay. And I'm trying to use the mouse here. Okay, there we go. Right, I'm going to go back a bit and I'm going to work forward. So sorry if I miss your comments here. Okay, so firstly, can I say thank you to the super chats? That's a couple of super chats. It goes a long way. So thank you very much. Okay, so it's great to have you, Stephen, Diadon, Killers, Sunsaver. Great. So I'm sorry I haven't been able to engage with you, but I kind of, because it was unformatted so much, I wanted to get through this material, because the connection between the replication that we appear to have achieved and the historical other work in the field, and then separately the discussion on the nature of ball lightning, this first introduction to this work by Bitchkov, I think is very key to bringing all of these areas together and really knowing what we are dealing about, knowing with certainty that this is what it is. This is science. It's very directed science. It's very focused science. It hasn't got this mishmash, and it's based on something that is absolutely part of nature. It's not a fantasy. It's real. It happens. It's been documented by thousands of people over humanity's existence. Hi, John Doe. So, okay. Yeah, you can weld with ultrasonics, Stephen. These blobs are like solids acting as liquids. Yes, kind of. That is exactly kind of what it is like. Yeah, I think they are electromagnetic, but it's kind of like it has substructure within it. And then when we go to look at the rest of the Bitchkov paper, you might kind of see why that might be occurring. Maybe not, maybe. Does the periodicity of the crystals correspond to the frequencies of the ultrasonics? I don't know. I think that it's I think the periodicity of the crystals actually is relevant related to the coherent matter waves within the overall coherent matter structure. And I think what you're seeing is the collapse of the wave and what it leaves behind as it does that. I think it's important though that they are orthogonal. You're seeing in physical nature, I believe, what actually is occurring when the matter is actually acting as one big wave. I think probably that's it's a reflection of it, or a symptom of it, I should say. Maybe not precisely what it is, because you kind of have to reorganize the ions on the electrons back into normal, ordinary matter. So there's great discussion on here on how to achieve it. So it's really nice to see. Yes, I do believe that either on the electromagnetic nature or the sound nature, which translates to electromagnetic nature through the ions, you could tune a greater or lesser outcome. There's also the thermal, which is also vibration. So you can have electromagnetic field fluctuation, and then you can have thermal phonon and thermal photons interaction, and also sound in the audio and subsonic and ultrasonic frequencies, but also light in frequencies. So I think it's a combination of various things that you would require, but it's all vibration, it's all oscillating matter, and it's about finding the right crossover of parameter space that gives you something closer to the outcome that you want. But I think what we can learn from what I've talked about today is that if you start with very light elements and heavier elements, your natural tendency is to end up with something in the middle, okay? And they will move in from their respective ends. Sometimes they basically combine and you find something dead in the middle in this process. However, if you're starting with something like titanium, it's kind of like, and you've got protein in there, you end up something that moves towards the protium, and the protium moves towards the titanium, but also because of some of the energy yield of fusion and the disruption within the coherent matter and the way that it settles out, you end up sometimes with some, if it's more intense, you get the production of fusion events. And so you can guide forward and backward through this. So Goldwater, what's his name? It's Alan Goldwater. And if you didn't know, he created the audio file format for the original audio format on the Macintosh. There you go, Alan. Basically, no one knows that, so there you go. He calls his lab Magic Sound, and I just think it's hilarious now because we realise that the magic of this process occurs through vibration, which is essentially sound, on whichever way you look at it. Sound is the core of all synthesis of matter and desynthesis of matter and transmutation of matter. So I just think it's wonderful that he has always called his work, whatever he's done, Magic Sound, but originally and even still today, he does audio recordings. He recorded a lot of quite well-known bands back in the day with some of the best sound recording equipment that have ever existed. And in fact, some of the investments he's made, I don't want to say too much, but were from repurposing the value in some of those sound recording assets to help with the research here. So thank you, Alan. This correlation between what happened in Japan and the analysis of that and what's happened with what's been produced by
David and taking on board the learning that we've had over the last couple of years to get to this point of convergence. It wouldn't have been possible if you had not done what you've done. So thank you, Alan. So David asks a while back, what did you miss? You can go and have a look at it later, but we're talking about your apparent replication. So Mescal says, can we talk about what natural reactions in the crust of the Earth would make transmutations? Go and look at some of the published work that are now in the Matsumoto book. He discusses some things about that. But basically, cavitation, any high intensity energy situations, and lightning. That's kind of what does it. And any kind of charge separation. So hi Corky, great to have you. Okay. David, don't apologize for your equipment. It's the most important thing here is doing and looking at what you've done in detail and learning from it. I'm just trying to find any questions. If you've got any questions you want to ask before I go, drop them down there. So Mescal says, reminds me of slow motion footage of nukes going off. See the cables vaporize in the spike that goes faster than the ball developing. Yeah, it's likely to be something similar, isn't it? Of course, it could be the intense neutron flare. And as the neutrons go into metal, they could, or whatever, they can cause them to fall apart. So Magic Sound is in the house. I don't know if people ask questions for him, but personal hero. Thank you, Alan. Yeah, magnetite would be a collector of monopoles. That's true. But in fact, so would any conductor. So copper, gold, anything. The book PDF I'll publish in the blog. That's a question by Killers. So Stephen Hall's off-topic question for anyone. Supposed I wanted to make an energized water containing stabilized EVO rings and pump that water into my hydroponic plants. What would you suggest? Two suggestions. One is streamer discharge, corona discharge onto water. There is a Russian group that have been working with a German group, and they're basically like you get from a plasma ball, but discharging onto water. And they find that accelerates growing of plants and so forth. So that's actually work that's actually been done and shown to do this. But also Shishkin used his cavitator, the one that can kill you with an hour's exposure to it. And this is like, it's made of aluminium discs, and it's kind of like, if you can imagine, it's got keyways cut into it that are, you know, one goes into like that, and that rotates around like so, and that produces a lot of cavitation. And he actually takes that water and he puts that on seedlings, and it appears to grow faster. So, but when that is operating, I definitely wouldn't be anywhere near it. But the water that you can get, obviously, it will have oxygen in there, and it will be able to bind the monopoles generated.
and you could then feed that, and also not just the monopoles, but the newly synthesized monoatomic elements that are produced, the fresh elements that are produced, just like they were produced in the Mars vibrator plates. So, but I would, I'd choose by taking rainwater or spring water and start with that. I think that would be your best bet overall. Rainwater, particularly rainwater after an electric storm. I would use that as your starting material. My dad, as a farmer, always used to say, the rain is much better than water out of the tap. And I never really understood it. But now I think I have a very deep understanding of why that is on a scientific level, and on a level that is relating to what the natural processes are rather than what the assumed natural processes are. Salt lakes are a source of crystal gold and most pure salt brine, sunshine, bacteria. Yeah, very likely. Yes, you're listening to Bull Lightning Radio on 10 on your AM dial. Yeah, probably. That's it. I think the fact that John Hutchison was doing that, we observed the same thing in our the Hanks Evo Blaster, on the first day of videos published about the Vega experiments, and the fact that it's in that prior publication on the nature of ball lightning. I think this is it. So that's how you would establish that you are creating the Hutchison effect type things. That's how you would assess it. I came across a mention that King Solomon also didn't mine gold, but made it with sacks of gold and salt in layers buried in the earth. Quite possibly. I'd like to see some of these. Sometimes these things look so bizarre, but there might be an element of truth in there. And with the new understanding that we're getting between us and can explore through experimentation relating to natural phenomena, we might get a better idea of what the recorded story, where the truth lies in that. Yeah, human evil is definitely designed to hide this technology. Grass better than snow shovel. Right, very good. Aluminium and potassium hydroxide don't get along, yeah. One dissolves the other very quickly. John Doe, I will publish that. He's asking, is the ball lightning information from the early 1900s from a book? Yes. As I said, it's from. Let's have a look. It's from Brandt's. I think it's Brandt's book. It's in Bitchkoff work, which is a review of historical work before they talk about theoretical
models. But the significant event was this work in 1923. Walter Brand's book, Ball Lightning, and it was published in 1923. And it was based on 215 ball lightning observations and descriptions from 1665 to 1919. So basically, Brandt had made all of these assumptions, these evaluations of the common features of a ball lightning by 1923. So yeah, Mescal, I've talked about the fact that exclusion zone water will occur in the cavitation structures, in the yin-yang structures that form in ultrasonic systems, and that because you have charge separation in exclusion zone, and also because in cavitation itself you'll get plasma forming. You have all of the mechanisms for spinning charge, which is charge moving over distance, which create a magnetic field. And this is, in my view, a self-reinforcing process. Okay, so I'm going to thank you all tonight. This was a review. We started off by talking about the fact that we have a catch-22 situation, which I was always aware of would be the problem with the Fukushima tritium water, 1.3 million tons of it. And it was really not surprise, but we have direction, and so we need to give them more data. What we need to do is to get to a point where they don't dismiss us on the fact that nothing can happen, but we need to get to a point where we can get access to enough of their water to prove that the process that we are able to replicate elsewhere is able to do what we think it will do when it comes to tritium water. And one of the suggestions I made to Dave, and I talked about earlier, was that we need to buy a whole bunch of deuterium, run it through one of these electrolysis systems to make DDO, and apply that to a sheet of Mn55, manganese 55, and see if we get iron produced, and then look to see if the iron is iron 57, and repeat the experiment with light water, and to see if we basically get iron produced, but the iron is actually iron 56. One will have magnetic resonance, the other one won't, and therefore we can prove that we can take a higher isotope of tritium, of water, a heavier isotope of water, and that this is likely to occur if we take again tritium, and if we do, you'd expect to get more iron 58 if you use tritium. But I think these experiments need ICP-MS and they need NMR, and we have enough difficulty getting access to SEM with EDS, but the problem being is a large stage in many cases, and or being able to analyze materials that are non-conductive in a non-destructive way, which you can do with field effect SEM EDS, but you can't do with the one that Alan has, which is limited what we can test in the samples that we have in a non-destructive way. So, for instance, the cauliflower, the yin-yang, the major yin-yang structure from one of the lions, that structure that I refer to, that's like this all the time, that beautiful structure. We can't look at that because it's in silicon dioxide. So I have it. And I would like to be able to look at it, but without destroying it, because once you've covered it in gold atoms or your silver atoms, you have a less chance to go backwards. You can't go backwards from that; it's done. So it requires immense amounts of patience to have a vision in your head of what you want to be able to test at some point in the future, should the opportunity arrive, and hope that not too much life passes in between. But you do what you can to take steps forward. So anyway, I would like us to get to a position where we've got enough published data that's repeatable, that we can then in various experiments that tell the same story that's already been out there in natural observations spanning hundreds of years and in scientific experiments and patents, but without realizing it's basically all the same thing, and then say, look, this should occur in the way that it seems to occur in every other instance, in the case of taking tritium and putting on calcium carbonate. There we go. And limelight's existed since 1820, so it's not something I'm trying to invent. It's not something you need to invent. It just exists. And so, yeah, we talked about the fact that we did share some data, but this isn't the data they're after. They're not interested in being able to separate the water and how much energy it would require. I think they want more on the transmutation side. So then we looked at the transmutation here, the analysis of Magic Sound Lab, and the fact that it was tip oriented, that the calcium and the carbon were co-located, and that is interesting in its own right, because we've seen that in so many other experiment key features, where you get, for instance, the calcium, the carbon, and the oxygen co-located in the structure, in the triangle, in one of the lions, and in the corner of the Cantal wire, and on that aggregation on top, where you've got those nitrogen, oxygen, and carbon type crystals being formed in the center of that vortex, and so on. And the fact that this structure here, this feature off to one side, has this kind of cardioid shape, has the type of elements that you would observe in that kind of thing, looks very similar to the structure that built up in the work of who is it? Claytor and Stringham, and they observed the same type of elements there. And when we were looking at this, we were seeing that it's out of the main area where this action occurred. And so if we look at it here, it's actually over here. So this is the main tip exposure, and this is this so-called inclusion here off to one side. And I believe this is what we need to look more of. And we saw something similar going on live when we took the videos, high frequency videos, high sample rate videos of the work with Slobodan Stankovic last year, where we saw these balls forming and they were kind of moving around and jumping around, and I believe that would be one of these balls that we've seen all the transmutation going on in this particular structure. And I believe if we do more work, we're just going to see this every time. And so there we go, and that was that work. And this was on the tip. And we talked about the fluid dynamics there, and the fact that it may be carbon that is come out, and then if it is carbon that's come out, why has it come out and not converted to carbon dioxide? But then we went to the Bitchkov work, and if I type in here, not radio, but I type in soot, they say here that can melt a metal and surround the molten place with soot, okay, which is carbon, and this is from 1929. So this is not a new observation that carbons comes out, but I think the first person that can credit it with it coming from an HHO system is what was in the patent and claims of Yule Brown from 1980s. Okay, but ball lightning was already doing it for all eternity. Okay, okay, and yeah. So then we looked at the titanium, and this was the Ohmasa gas observation, and the fact that it was in this bubbly blob that was on the main affected area, and inside that bubbly blob we had these micrometric crystals with open voids formed. And that's the same kind of thing if we find it here. This one, is it? Yes. This was observed in the what I consider a replication by David Boutelier. And again, it's this bubbly structure, which I would suggest is this surface tension wetted together multiple ball lightnings, or itonic clusters as Matsumoto would call it, and even Matsumoto talks about this kind of wetting together, and we have that on this structure over here. So it is the same thing everywhere you look at it, if you have the eyes to see. And inside of the structure where the action is occurring, I believe that there is some fissioning going on here and some fusion, and that is why you see some elements that are fusing and other elements that are fissioning, and I gave the reactions that would occur, and that was already observed by Roitskev et al. In the early 2000s, and that Roitskev et al. In that work connected all of the features of ball lightning being able to travel down wires, as discussed in those historical accounts, presenting the atoms synthesized, and the atoms are either lighter than titanium or heavier than titanium. This is the making, and this is the breaking of the titanium-48, and that the ball lightning that came out had the spectrum of both lighter and heavier elements within it. And there we go. So I think that's probably enough for tonight. So thank you very much for your time. And next week, like I say, I in this Bitchkov paper, which I will give a link to in the blog later in the week when I start, I'll lay down some of the other items, images and stuff in the blog. But I can say that I was, and like I say, I'm only part of the way read through the theoretical part at the end, but I almost couldn't believe it. And the way I came to find that Bitchkov paper, you wouldn't believe it either. But anyway, I'll discuss it. And it is how it's happening. It's just how it's happening. It's just, you know, you constantly realize that you're not discovering anything new. But what is discussed in the theoretical section of that Bitchkov paper are structures that they've theoretically calculated should be there, but we've already physically shown those exact same structures indelibly and permanently in the Vega Valley, and made the conclusion that it should be this, and then you have this theoretical paper which is suggesting that it should be this, and we should see these things, and it's just beautiful. It's just beautiful. Okay. All right, so I'm going to say goodnight now. Thank you very much. Thank you, Eric. Thank you, Corky. Thank you, Simeon. Thank you, David. Hats off to you, David. Hats off to you, Alan Goldwater. Justin Forder, see my note earlier about source of triated water. Great. If anyone's got a place we can get some triated water, that would be absolutely fantastic. So please note that also in the blog at remoteview.icu or in the comments to this YouTube video. But buenas noches, sayonara, dobro noc. I will see you. Bonne nuit.